Hey everyone, can you see me? Can you hear me? Yoo-hoo. Let's put it here. Oh, sorry. Hi everyone. Everybody, can you hear me? Can you guys hear me? Oh yes, okay, that's good. Okay, thank you. Okay, great. So let's get started with the practice sheet. Okay, I'll go fix it. There's a button here, right? We have button up. Oh. Oops. Okay, so let's start with we're gonna do practice on rings. The board is clear. Yes. Okay, so please pay attention to it. Okay, so let F3 be the field with 3. Let's write this down. And let R equal F3 of X. Okay, denote the ring of polynomials. Can you guys see? Yeah, they can see. Okay. Great. Let's shut the door. Let R equal F3 of X denote the ring. Denote the ring of polynomial whose coefficients in F3. Did you guys try these or not? Yeah, did you try them? Yeah, okay. If you didn't try them, then I'll give you like 1 or 2 minutes to try the question. Polynomial with coefficients, and F3. Let f of x is x3 plus x squared plus 1. And g of x, what is g of x? Is x3 plus 2x squared plus 1. Let I be f of x, the ideal generated by f of x. And j, g of x, right? First question. How many elements do R mod I and R mod j have? And show that R mod I or R mod I and R mod j isomorphic rings. Isomorphic as rings. Great. Great. So, how do we start? What is the first question? How many elements does R mod I have? How many elements? How many elements does R mod I have? Yeah. How many elements? Everybody? How many elements? 3 to the power 3. We see that or not? Yes or no? Yeah. Yeah. That follows from our class theorem. If f is a finite field and f of x is a polynomial of degree n, then f of x modulo f of x, and big f of x modulo little f of x has f to the n elements, right? Yeah.
Even if it's not irreducible?
Even if it's not irreducible, exactly. The proof that we gave, I mean, we gave a proof of this fact last time, right? But the proof is the same if it's whether it's irreducible or not. Okay, so 1 R mod I and R mod J have 3 to the 3, let's say cardinality of F3 to the 3 elements. Okay, are we good here? Now, are R mod I and R mod J isomorphic as rings? People in the chat are welcome also to participate. Yep.
No, because R mod A is not a field. And
R mod I is not a field, and R mod J is a field. Let me see. So R mod I is not a field, right? You plug in 1. And here, let's see, plug in 0, you get 1. So X plus, yeah, that's right. Okay. But why? Okay, let's justify. Why is R mod I a field? Sorry, why is R mod I not a field? Why is R mod I not a field?
Because that polynomial is reducible.
Exactly, very good. F of x is equal to x cubed plus x squared plus 1 is reducible since it has degree 3 and f of 1 is 0, right? You can factor it into a degree 1 times a degree 2, exact, right? So f of x is equal to x minus 1 times g of x over g, a of x, where a of x and f3 of x has degree. What's the degree of k? 2, right? So this polynomial is reducible. Hence, R mod I. Hence, R mod I is equal to f3 of x modulo the ideal generated f of x is not a field. Very good. Very, very good. Yeah.
That's right. That's F2. F3.
F3? Did I say F3 or F2? 3. Yeah, F3.
Yeah.
Okay. Oh, you mean here? Here it's here?
Yeah.
It should be 3. Yeah. Okay. Now, why is R mod I a field? R mod J a field?
yes,
Yeah. And how do you justify that in that case?
you have 0, you have 1, you have 2, you have 0.
Yeah. Okay. That means it has no roots. But why can I say it's irreducible? In general, does a polynomial that has no roots, does it mean it's irreducible? Or do I have to look at the degree? That's a very important step. So the first step, to check that it has no roots. That's a very good step. Very good initiative to take. Show that G has no roots. But why does that tell me it's irreducible? What is it here? Oh,
In degree 2 or degree 3.
in degree 2 or degree 3. If it has no roots in degree 2 or degree 3, if a polynomial of degree 2 or degree 3 over a field has no roots, then it's irreducible. Remember this theorem? Yeah. In the final, if you have a question like that, you should justify this. I should see that you're using that theorem. Okay? So u of x has no roots in F3. Since what is g of 0? G of 0 is 1. G of 1, what is g of 1? G of 1 is 1. What is g of 2? G of 2 is 2, right? 2 cubed. What is g of 2? I think it's 2, right? Did you try it? What is g of 2? So 2, this is 3. 2 squared is 1. So 2, 3. Yeah, 2 cube is 2. So g of 2 is 2, right? You guys see this or not? You guys see this? Just plug in 2. 2 cubed, that is 2 cubed mod 3. 2 plus 2 cubed 4 plus 1, 5, 2. Okay? Now, since g of x has degree 3, this is the most important step. And g of x is irreducible. Okay, very good. F3 of x. So R mod J is a field. So R mod I is not isomorphic. R mod J, because one is a field and the other is not. People attending online, questions? Can you see the board clearly? Yes, okay, great. Any questions? Any questions here? Yeah.
Would we, if we didn't say, so f of x is equal to x minus 1 minus k x squared?
Yeah, no, you don't. Because if you have a polynomial of degree 1, it has a root, but it's still irreducible. Okay? This is
We
it.
don't-
No, I mean, just right. Just it has a root and it has degree strictly bigger than 1. Okay? Just sort of to avoid that thing. Because if a polynomial has degree 1, it's irreducible and it has a root. That's the only polynomials, that's the only irreducible polynomials that have roots. Okay? So you won't get a lot of marks off for this. Like, if I'm in a good mood, I'll just like let it slide. But this, for example, even if I'm in a good mood, you'll get half the marks off. More than half the marks off if you don't say that it has degree 3. So it's irreducible. Okay, this is the most important step. Okay?
We say
Here, as rings. Now, as additive groups, are they isomorphic or not? By the way, that's a nice question. As groups under addition, are these two rings isomorphic? As these two groups isomorphic? The groups of these two rings, the additive groups of these two rings are isomorphic. And they are isomorphic to what group? To Z mod 3Z cross Z mod 3Z. Okay, try to think about that. Okay. Try to think why the groups under addition. Let's forget the ring structure of R mod I. As groups, they're isomorphic to Z mod 3 cross Z mod 3. Okay, try to think about that. And let's go on to the next question. Okay, any questions about this? About this question? Yeah.
What about it that it has degree 3 means it's irreducible? If it's irreducible, it means you can't, it's like not factorizable.
You cannot factorize it, that's right. But if you have degree 2 or degree 3, being irreducible is equivalent of having no roots.
Yeah.
But if you're in degree 4, for example, you can still have a degree 4 polynomial that is a product of 2 degree 2 polynomials, each of which has no roots, but that's reducible.
Yeah. But it's just because it has degree 3, that doesn't immediately mean it's not irreducible, because
It has degree 3 and has no roots. Degree 3 and has no roots implies it's irreducible. Okay? You cannot factor it further. If it had, so suppose you want to factor a degree 3, non-trivially. What would the possible degrees of the factor be? 1 and 2. Right? So if you have a factor of degree 1 means you have a root. You see that? So for degree 3 and degree 2, having no roots in the field F is equivalent of being irreducible. In higher degrees, that's not true. Okay? Yeah? Great. Any questions about this? This is a typical question. This is a typical question on the exam. Is it hard?
Could we have a polynomial with degree higher than 3?
Yeah, we will see one example now. That is irreducible, you mean?
Or read that?
Or reducible or irreducible. Yeah, yeah. Sure. Okay, great. Any questions? People attending? Oh, someone has a question. What is the first line on the third board? So f of x is x minus a times k of x, where k of x belongs to f3 of x as degree 2. Okay? Great. Awesome. This is a difficult question. Would be worth 5 or 10 marks. The statement is longer than the answer. Okay? So let's do more. Should I do question 2? Question 2 I did in class yesterday. Question 2 I did in class, right? Yeah. You guys have the questions with you. So let F5 be the field with 5 elements. Construct a field K with 25 elements. What is the characteristic of K? And let GT be equal to the 24 minus 1 in K of T. How many distinct roots does G of T have in K? That I did yesterday in class. Okay?
Yeah, I think the characteristic.
I didn't do the characteristic part. What is the characteristic of that field, of a field with 25 elements? 5, right? Yeah. Okay. If you want me to do it, I can do it. Do you want to go through it again? Should I go through it again? Let's go through it again. So construct a field. Two. What is the characteristic of K? I mean, that here you can do it more generally. Okay, but here I'm asking you to prove it for this particular K. But here, if you have any field with 25 elements, then it must have characteristic 5. Okay? 3, let G of T how many roots? Does G of T have? Okay, here K just the polynomial is a change variable. Okay, instead of X, I put T. Okay, great. So how do I construct a field with 25 elements? Anyone can help? Yeah.
You pick an irreducible polynomial. Like you can plug it in. Oh, of degree 2 because 25 is equal to 5 squared.
Yep.
Yeah.
An irreducible polynomial of degree 2 over what field?
F5.
Exactly. Very good. I pick an irreducible polynomial of degree 2 over the field F5. And for it to be irreducible, what do I need to check? What are the two conditions that I need to have? What is the condition that I need to have for degree 2? Exactly. So if the polynomial is of degree 2 over F5 and it has no roots in F5, then it is irreducible. Then it is irreducible, right? Let's do this. Very good. I mean, and the final, say for example, you have a blank. Just write what you know. Right, okay. So even if you don't find the polynomial of degree 2, I tell you construct a field with 25 elements. Just say, okay, start with F5, find an irreducible polynomial of degree 2, find a polynomial of degree 2 in F5 that has no roots. That will get you some points. Okay? It's better than writing it's better than writing nothing. Okay? Even if you don't find the polynomial, but just say how you do it. Okay? Great. Now, how do we find the polynomial of degree 2? That is irreducible.
like all the 5 squares.
Exactly, very good. So 0, 1, 2, 3, 4. Now this is a and a squared. So 0 squared is 1, 1, and then 4. 3 squared is 4, right? Square is symmetric. So and 2 is equal to minus 3. So you just copy this down, right? 3 is minus 2. So when you square them, you get the same answer. 4 is minus 1. So when you square them, you get the same answer. Okay, so do I have a square? Do I have an element whose square is 3 or not? No. Do I have an element whose square is 2? No. So for example, x squared minus 2. Does it have any roots in f5 of x? In f5, sorry? X squared minus 2, which is equal to x squared plus 3. And f5 of x has no roots in f5. You agree with this or not? Everybody, do you see why? Everybody, yeah. F5. F5 is Z15. Minus 2 is 3. Right? Yeah? Is it clear? What is F5? F5 is Z15Z. Minus 2 is equal to 3. In Z15Z, 5 is equal to 0, right? Yeah, 3 plus 2 is equal to 0, so 3 is equal to minus 2. Okay? Yep.
But just curious, like why
Why do I write them both?
yeah.
Yeah, it's just because it's easier to see that a squared cannot be equal to 2. That's it. Usually we present them in reduced form. You present them between 0 and 4, the numbers. But it doesn't matter. You can just say x squared minus 2. That's not wrong. Yeah.
Does it not work to take x squared plus 2 and x squared
Yeah.
minus 3?
X squared minus 3 is also irreducible. Has no roots in 5. Very good. Okay. Since, which one do you want to work with? First one, doesn't matter. Since x squared minus 2 has degree 2, it's hence irreducible and no roots. And no roots in F5. It's hence irreducible in F5 of x. So how do I construct my field? How do I construct my field with 25 elements? Anyone can help me? Someone else? Anyone can help? Anyone who hasn't spoken today? In the chat? With x, yes, Nicholas, yes. Yeah, anyone wants to help, whether in the chat or in here? Yeah.
F5 mod x.
F5. So F5 x mod x squared minus 2 is a field with how many elements? Is a field with the cardinality of F5 squared, which is 25. Okay. Very good. Very good. Oh, that's reassuring. That's good. I'm getting good answers. It's easier than before, right? It's way easier than before. Yeah.
Is there a reason you change it to like plus 3 and plus 2?
Usually you just write them with reduced coefficient. You write them from 0, 1, 2, 3, 4.
So you don't want like a negative.
Exactly, but it doesn't matter. I mean, you don't have really negative and positive here,
Yeah.
right?
Would you take marks off if we did like minus 3?
Okay, great. Question. Now, what is the characteristic of K? 5. Why is that? Why is it 5? What is the characteristic? It's the additive order of the 1. What is the additive order of 1 here? Of 1 plus the coset x squared is 5, exactly. Very good. K has characteristic 5. Now, just meanwhile, like while I'm erasing the board, can you have a field with 10 elements? If I tell you, does there exist a field? Can you construct a field with 10 elements or not? No. Why? Exactly. Very good. Very good. Very, very good. See, I left the easier things till the end. You know, this is easier than the other stuff that you have been doing. This is at the end. Okay, great. So M5 and review with 25 elements. What is the characteristic? I mean, do you want to do it more generally, or do you want to do it with this example? So I told you what's the characteristic of K? It's the K that you found. Now, any K, with any field with 25 elements, the characteristic will be 5. Do you want me to show that for generally, or in this particular case? Generally. Okay. Now, what is, this is a perfect question. Let K be a field with 25 elements. What is the characteristic of K? Okay, what's the definition of the characteristic here? Yeah. Sure, that's good. And then what else can I say? I want to do it with something else. That's true. Like you can do it with the additive order of the identity, but what's the definition of the characteristic? Because in general, if you have characteristic 0, the definition of additive order of identity doesn't work, right? But what's yes?
For the homomorphism from Z to the ring that
Yeah.
you're finding the characteristic of, it's the like coefficient of
The generator of the
of the kernel.
exactly right. So let K, if K is a field with 25 elements, let phi from Z, let phi denote the unique ring homomorphism from Z to K. Now, 1 in K has finite order. Has finite additive order because it has order dividing 25, right? Since K has size 25, or since K is finite actually, the kernel must be nz for some n's bigger or equal to 2. Right? Let's do that. Since K is finite, we can do it in many other ways. Since K is finite, here phi is equal to nz for some n, for some integer n bigger or equal to 2. Great. Now, how do I conclude that this n must be 5? This is a good review of characteristic because these are arguments that you use. These are arguments that you use. I'm pretty sure you've seen this argument before. Yeah.
The first isomorphism theorem identity. Subgroup of field.
Is that something?
So it's a subgroup in the domain, so
it's
P and I mean it's a prime.
It's a prime, and it's not 0. Right? Because if it's 0, you still get an integral of it. Very good. Very good. So Z mod NZ is isomorphic to a subring of K. Now K is a field. Only 5 elements. Now a subring of a field, what can I say about the subring of a field? A subring of a field is an integral domain. Field with 25 elements. So K is a field with K is a field with 25 elements. So Z mod NZ is a finite, is isomorphic. Is isomorphic to a finite. You know what? So hence K is a field with 25 elements. Z mod NZ is isomorphic to a subring of K. So Z mod NZ is a finite integral domain. Now, what can you say about finite integral domains?
They're fields.
Very good. So Z mod NZ is a field. So N is equal to P for some prime number. Now, why is that P5? A bit longer than the shortest possible answer, but this is good review for you. Okay? This is good for you. This is good review. Now, why is P equal to 5? So I proved that Z mod NZ. I mean, you guys know that this is a theorem from class, right? If you have a finite field, then the kernel of the homomorphism is PZ. Right? This is a theorem from class. I could have used it immediately, but I just rewrote the proof just to refresh your mind a bit. Okay? You realize it's a theorem from class. If F is a finite field and Z is a homomorphic, then the kernel of the unique homomorphism from Z to F is PZ for some prime number P, right? This is a theorem from class, so I could have used it here, but I just decided to do it again. So N is equal to P for some prime P. Why is P equal to 5 here? Why is P equal to 5? Yep. So by Lagrange's theorem, hence Z mod PZ is isomorphic. Not only, well, it's isomorphic to a subgroup of K, additively, of course. So P with the size of Z mod PZ divides the size of K, which is 25. This is P. What's the prime number that divides 25? Okay. I could have used the theorem immediately here. I could have used that K is a finite field from class. I know that the kernel of the homomorphism is PZ for some prime number P. Okay, and I wouldn't have to do this. But that's a good review. Okay. I reviewed also characteristic of it. The proofs of characteristic. When is oh, okay, yeah, okay, thanks. Oh, yeah, I'll repeat that. Okay, any questions? Yes. Look, every non-zero element in a field is a unit. Okay. A field has 0, yeah. T24.
Yeah.
I'll do it now. This is done. Okay, I'll do it now. Okay. Yeah. Question? You had a question? You had a question? No. Anybody had a question on this? Okay. People attending online, do you guys have questions? No. Okay. Oh, can you answer why we cannot have a field with 10 elements? So in class, we proved in one of the lectures, maybe in Mondays, like I don't know when, but we proved that any finite field must have order p to the n for some prime number p. So if you have a finite field, then it must have order p or p squared or p cubed. So you can have a field with 25, 125, 7, 49, only prime powers of prime numbers. Now, we didn't show that for every prime power you have a field of that size, but if you have a field, a finite field, then it must be of that size. Okay, great. Is this clear? So please, this argument, no, very good. Note the arguments like that. All the characteristic arguments, by the way, all of them are like this, right? Realize this or no? They're all like that, right? Okay. Now, let G of t be t to any 4 minus 1 in K of t. How many roots does G of t have? Anyone can help me with this? First of all, is 0 a root of this or not? 0 is not a root because 0 minus 1 is minus 1, which is not 0. Great. That's one less. So I have to check 24. How many roots do I have for this polynomial? $24? Yeah, why?
Because 25 minus 1 is 24. And
Very good. But why?
you can explain it.
Okay. We do have 24 roots, yeah. But why is that? Yeah.
Well, I'm gonna just put this.
That's okay. Yeah, say.
K, that set has 25 elements, right? And
Yeah.
so if you minus the 0,
Yeah.
that's like K to the X, which isn't that the unit?
Yeah.
Okay, units of K. And so the size of the units of K would be 25 minus 1, and that's 24. So it would be 24.
Okay. Very good. Very good. Yeah.
And the units are
Exactly. And then what more? There's one line we could finish. So we have a group of order 24. Very good. We know it's a group. It has size 24. Exactly. Okay. Very good. Very good. Very good. Is it clear or not? Okay, so should we know how to prove that a field? Yeah, I think you should know how to do that. No, this is in the characteristic part. No, that a field has prime power order. It's not in the characteristic part. Yeah, it is in the characteristic part. No, yeah, it is. I wrote it. Definitely, I wrote it. Definitely, I remember writing it. I remember writing it. I think so. I don't know. I don't know what lecture it is. But that's how we did. How did you do that with Cauchy's theorem, right? We did that with Cauchy's theorem. That if a finite ring has prime characteristic, right? If a finite ring has characteristic p, then this finite ring has order p to the n for some n in n, right? You remember that? Yeah. Great. Now, how many roots does G of t have? Very good. So K is a field. This means that any non-zero element has a multiplicative inverse. Hence, K minus 0 is a group under multiplication. How many elements does this group have? K minus 0, how many elements does it have? With 24 elements. Now, really, you can see that this group is cyclic, actually. This is Z mod 24Z in this case. We didn't see that, but, you know. Okay. No, we could prove that part. Yeah, no, we can prove that, but that's okay. We won't do it here. So under multiplication with 24 elements. Hence, for any let's say A in K minus 0, A to the 24, an element raised to the power to the order of the group gives you the identity of the group, right? What's the identity of K minus 0 under multiplication? 1. A to the power 24 gives you 1. Hence, and since G of 0 is equal to minus 1 is different than 0, then G of t has 24 distinct roots. Okay. Are we good here? Any questions on this? Any questions? People attending online, any questions? Are we good here? Yeah. Exactly. So if g of 0 is 0, then it would be 25. But just check that g of 0 is a root so that you have exactly 24 elements. Okay? Yeah.
And what's wrong with having 25?
You could, but this is not. G of 0 is not 0. Right? Yeah. If you replace it by, if you multiply g of t by t, so say you get t to the 25 minus t, you get 25 elements. Right? So say you multiply g of t by t. What example did I do yesterday? T25 minus t, or yeah. Okay, yeah. So I mean it's the same thing. So say you multiply this one by t. Okay? Every non-zero element is a root of this one. Of t to the 24 minus 1, right? And 0 is a root of t. Right? So you get 25 roots. But for this one, you have exactly 24. Every non-zero element is a root. And exactly this. 0 cannot be a root because g of 0 is minus 1. But if you multiply this one by t, the whole thing by t, g of 0 will be 0. So 0 will be a root. Okay? Great. Questions? Questions? No? Okay. Exercise 3. Find all irreducible polynomials of degree 4 with coefficients in F2 to deal with 2 elements. The Jews at F2, oh man. Oh man, okay. Can I write this? I don't know what I had in mind. Okay, great. Let's see. It's gonna be a thing. How many do we have? Yeah, I think we have 3 of them, right? We have 3 of them. 3 irreducible polynomial of degree 4 in F2. That's a yeah. You see that? No? Okay. No. Pardon me? Yeah, but you have 3 of them. 3 irreducible polynomials of degree 4 in X2 in F2. Okay, so fine. This is a nice question. Find all irreducible polynomials. X3. Part 1. Find all irreducible polynomials of degree 4 and F2. Okay. So first, let g of x be an irreducible polynomial of degree 4. We will just write down the possibilities for g. We'll just start eliminating. Let g of x. Now g of x has degree 4. What can I say about the highest coefficient? It's x4, right? What can I say about the coefficient of x4? It's non-zero, right? What must it be if it's non-zero and I have in F2? I have 2 elements, 0 and 1. If it's non-zero, what must it be? 1. So g of x is of the form x4 plus ax cubed plus bx squared plus cx plus d. Right? Yeah? Now, what are the conditions that I need to satisfy? What does it mean to be irreducible? It means, yeah?
No roots in degree 2 or 3.
No, but this is degree 4, right? Yeah.
Guarantee that you
That's the question. That's the question. How can you factor it? How can you factor a degree 4 polynomial? So all you want to do is eliminate all possible factorizations, right? You don't want to factor it. How can you factor it? Degree 1, degree 3. Agreed? That's one way. What's another way? 2 and 2.
You can't.
Well, now degree 1 and irreducible of degree 3. That's the way you can factor them. Right or no? You guys see that?
So.
It's irreducible. Do we see this or not? So what are the ways you can factor g of x? Degree 1, irreducible of degree 3. Right? If g of x, so case, if g of x is reducible, then so first you need to have no roots, right? Well, let's not do that. So if g of x has a root, this is a bad calculation. I don't know why I put it. I don't know what I was thinking. If g of x has a root, then g of x is not irreducible. Okay? Agree? If it has a root, then it's not irreducible because you can factor it. So what is g of 0? Can g of 0 be 0? No. So it must be, you have two elements. What must it be?
Did you say that that was just for in degree 2 or 3?
No. This, if g of x has a root, then g of x is not irreducible. That holds for all polynomial of degree 2 and 3. But what holds for degree 2 and 3, if g of x has no roots, then it's irreducible. Okay? Now what can I say about g0 here? Is it too hard? Is this question too hard? Is it too hard? What can I say about g0 here? g0 is what? 1. g0 is 1. This implies that d is equal to 1. If g is irreducible, then okay, so now I have a form. I have a form of g. The g of x is x4 plus ax cubed plus bx squared plus cx plus 1. Great. Now, how can I factor g of x? Well, what must g of 1 be, by the way? G of 1 must be equal to 1, right? G of 1 is different than 0. So g of 1 is 1. Great. So 1 plus a plus b plus c plus 1 is equal to 1. So 1 plus a. So this means that a plus b plus c is equal to 1. Agree? Great. Now, if you want to factor g of x into irreducible polynomials, okay, let's say they're irreducible of lower degree. So either g of x is irreducible itself, right? Or you can factor it degree 1 and degree 3, where the degree 3 is irreducible. So in this case, it must have a root. Or you can factor it into 2 degree 2s. So degree 1, degree 1, degree 2. You see that or not? Yeah? Where it has 2 roots. Or you can factor it, let's see, so you can factor it 1, 3. It has a root. If you can factor it, degree 1 and degree 3, then it must have a root, right? Or you can factor it 1, 1, 2. It also has a root. And, or what can you factor it if it's reducible? Degree 2 times degree 2, where this degree 2 has no roots. Right? You guys see that? Factor a degree 4 polynomial. How can you factor it? 1 and 3, where the 3 has no roots. Right? 1, 1 and 2, where the 2 has no roots. Or you can factor it into 2 and 2, where this 2 has no roots. Or you can factor it into 4 and 1 if this polynomial is irreducible. Right? Yeah.
Are you allowed to have 4 polynomials with 4 roots of like thingy 1?
Yeah. Can you have 4 roots? How many roots do you have at most in F2? 2.
Oh, of course.
You cannot have 4 roots.
It's like modular sort of
It's like
mod sort of.
exactly. So it's like you have 2 elements. You have only 2 roots. Or you can either have 2, 2, where each of them has 2 roots, where each of them has a root. So it could be x squared, x minus 1 squared, basically.
So you can't have 1, 1, 2 then.
1 root.
Yeah.
1 root. And no roots. You could have that, but it doesn't hold in that case. Right? This is a hard one. You won't have to worry about that. Okay? You won't have to worry about that. If you want, you can continue doing it, but you won't have to worry about that. Especially on the final. Do you want to leave it or we can continue? No. I'm gonna ask you like, I mean, this is F2, the simplest case. This is the simplest field. And then if you want a polynomial of degree 4, so all you have to worry about is that it's not irreducible. All you have to worry about is that it has no roots. So all you have to show g of x is irreducible. I'll leave it to you in F2 of x. If and only if g of x has no roots and g of x is different than x squared plus x plus 1 squared. This is an irreducible polynomial of degree 2. Right? Now you have to worry that g of x is not the product of this by itself. This is the only irreducible polynomial of degree 2 in F2. X squared plus x plus 1 is the only irreducible polynomial of degree 2 in F2 of x. So you have to also worry that g of x is different than this squared. It's not a product of these 2 squared. So what you have is that g of x if and only if g of x has no roots and I mean, in tomorrow's lecture, we'll see something that we call the freshman grades. Okay, did you guys see it before or not? Okay. Do you guys know the formula for a plus b plus c squared or not? It's a squared plus b squared plus c squared plus 2ab plus 2bc plus 2cd plus 2bc, right? A squared plus b squared plus 3 plus 2ab plus 2ac plus 2bc. Agree or not? A plus b plus c squared, right? You guys know this formula or not? A plus b plus c squared is a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ac. That makes sense, right? You have twos. What is a plus b squared? Is a squared plus b squared plus c squared. Is a squared plus b squared plus 2ab. Right? Now you're working in mod 2. All the twos will cancel out. So you can just square all the elements. And g of x is different than x4 plus x squared plus 1. So it's equivalent to saying that g of x, what's has no roots mean? Means that a plus b plus c is equal to 1. So g of x is x4 plus ax cubed plus bx squared plus cx 1. And a plus b plus c is equal to 1. And g of x is different then x4 plus x squared plus 1. And then you get 3 choices. Yes. Please. That doesn't because you can have b equal 1 and a equals c equals 0. That's not irreducible. Right? That's this one squared. Okay? I mean, let's finish it. What can you say about ABC? So you have a plus b plus e is equal to 1, and ABC is different than, let's see, 0, 1, 0. How many choices you have? You can have a equal 1. How many choices you have here? You can find them. A equal 1, B equal 1, C equal 1, right? Or this means A equal 1, B equal 1, C equal 1. Or A equals 0, B equals 0, C equal 1. Or A equal 1, then what? B equals 0 and C equals 1. Yes. Yeah. And that's it. Can you find one more? C equals, what did I say? C equals 0. Yeah, that's right. That's right. Could you find more? I don't think so. I think there are only 3. I know before there are 3. Yeah. Oh, if it's irreducible, can you factor it into further degree 2? No. Now, this is the only irreducible polynomial of degree 2 in F2. So all you have to worry about, besides having no roots, that it's not the product of 2 degree 2 polynomials that are irreducible. Because then it would not be irreducible. You'd be able to factor it.
I thought you
No, irreducible means you can factor it into smaller degrees. That doesn't. For degree 3, irreducible is equivalent to having a factor of degree 1. For degree 2 polynomials, irreducible is equivalent to having a root. Okay, great. And I think how many polynomials you have? Those 3. So it's x4. Let's say them. It's x4 plus x cubed plus x squared plus x plus 1, and then it's x4 plus x plus 1, and then it's x4 plus x cubed plus 1. Those are the 3 irreducible polynomial of degree 4 in F2 of x. Okay. Why can't b be 1? Where? So if b is 1, no, b it can be 1. But you mean b equal 1 alone?
Yeah.
Because if b is equal to 1 alone, then you will have g of x equal to this. Right? If b is equal to 1 alone, then g of x would be equal to that thing. So it's not irreducible. Yeah, exactly. No, this is the key part. The key part is that you have to worry that it has no roots, and you have to worry it's not a product of irreducible polynomials of degree 2. Now, luckily in F2, you only have one irreducible polynomial of degree 2, which is this one. So you just have to worry that it's not the square of this one. Okay?
If it's the square of that, then you're chilling.
If the square of that, then it's reducible.
Yeah, but mod 2 still.
No, that here doesn't have to. The roots here doesn't have here mod 2 doesn't play a role. I mean, it plays a role that this is the only irreducible polynomial of degree 2 in F2. So an irreducible polynomial of degree 4 is a polynomial of degree 4 is irreducible if and only if it doesn't have roots and it's not the product of irreducible polynomials of degree 2. Okay? Then all you have to worry about here that how many irreducible polynomial of degree 2 in F2 you have? It's only this one. So you just have to worry it's different than this one squared.
But remember when you were saying you can have two roots that are degree 2, but they are not reducible. They are irreducible, and that
Two roots, no. Once you have a roots, then it's not reducible. It's not irreducible. Once you have two roots, then it's not irreducible.
reducible.
So if you want to factor it,
Yeah.
okay, what would the factor be? You have degree 1 squared and degree 2. So in other words, if you want to factor it, either the factorization will contain a polynomial of degree 1 to some power. So either it will have a root, or it will be yeah, that's right. That's right. Or it will be a product of two reducible polynomials degree 2. Yeah, that's right.
Yeah. So
Yeah.
that's right.
Yeah, that's right.
Yeah.
Now, what's the only reducible polynomial of degree 2 in F2? It's this one. Any other polynomial is reducible of degree 2 in F2 of X. Okay, check that. I think this is too hard. I don't know what I was thinking.
I will find out irreducible.
Irreducible. Yes. Yeah. Okay, I don't know why I was thinking when I put that question. I know that there are only 3. So if you can figure out later next term, you'll see how to count these. And you can see that there are only 3. Okay. So there are only 3 reducible polynomials of degree 4 in F2 of X. You don't have to know this. But anyways. Okay, great. Construct a field with 7 cube elements. Do I really want to do that? Let's see. You know, let's do that. Okay? Let's do that. Let's do that. And write down the units and the 0 divider in the ring at 5 of X mod X squared. Oh, there's something I should do more is try the exercises I give. Try it. Yeah, try that in my head. No, this one is nice. This one is nice. This one is nice. Don't worry about it. This one is nice. This one is nice. X4. Construct a field with 7 cube, a field K with 7 cube elements. This is part A. I'll add a part B now. Does there exist? Seven cube. Yeah. Does show that p squared plus 1 in K of T is irreducible. In K, T, C, construct a field with 7 to the 6 elements. Yes.
In the last question, there was also, it said show the multiplicative inverse of like X plus X. Do we need to know like multiple?
Yeah. So okay. So what is the multiplication? What?
X plus X to the 4th plus X plus 1.
X mod X4 plus X plus 1. Yeah. So find the inverse of X. This is not bad, right? Why is that? So you have X4 plus X plus 1 is equal to 0. Agree or not? It's congruent to 0 in this ring, right? In the quotient ring, X4 plus X plus 1 is congruent to 0, right or no? Because you're modding out by this ideal. Yes or no? Yes? Yeah? Let's write it here. Find the inverse of X plus I and factorials X on I, where I is the ideal generated by X4 plus X plus 1. That's the question? That's the question, no? Yeah. Okay. What can you say about X4 plus X plus 1 and I? Modulo I. It's congruent to 0, modulo the ideal I, right? Agree? Yes? x4 plus x plus 1, does it belong to the ideal I? So it's congruent to 0 mod I. Yeah. I give it. I give in f2 of x modulo x4 plus x plus 1. Well, I mean, the quotient ring is the ideal, right? Yeah, by the ideal generated by x4 plus x plus 1. Yeah. Okay, then what do I say here? So what is x4 plus x congruent to? Right? Because -1 is equal to 1. Agree or not? Now, what is x? Let's try to factor an x out. Factor an x out. What do you get? X times x cubed plus 1. It's congruent to 1 mod I. Agree or not? So what's the inverse of x? It's just x cubed plus 1. Okay? Is that clear? Should I write this or that's good? That's good. The inverse of x plus I is just x cubed plus 1.
That's what it's.
Since 1 is identity. 1 is the multiplicative identity.
Yeah.
Okay. It's just the same idea working mod 5 or mod p or mod whatever. Just working modulo ID. Yes. F2. So the coefficients are in F2. This one belongs to F2, right? So this one is equal to -1. This is a coefficient. Okay? Yeah.
Would you say that the inverse of x plus I is x cubed plus I or plus 1 plus I?
Yeah.
Okay.
Is it clear or not? Yeah? Okay. Great. Now that's a good that's an important exercise. This is nice. Let's see how to do that. So construct a field K with 7 cube elements. How do I do that? I need a volunteer. How do I do that? Yes, okay. I'll do my best. I'll do my best to repeat. But usually my answer is yeah, so the inverse of x plus I is x cubed plus 1 plus I. Okay, this is what the question. And I answered yes. Okay, great. Now, construct a field K with 7 cube elements. How do we do that? Who wants to volunteer? Someone? Yeah? Yeah, where? In F7 of x. Very good. Let F7 be the field. 7 elements. And what I need to do is to find an irreducible polynomial of degree 3 in F7. Great. Now, what's your chance? How do you find one? Yeah.
Can we say that we know that 7 is a prime congruent to 3 mod 4? And then.
Yeah. No, that's for degree 2.
Oh, that's only for degree.
Yeah.
2?
So you have 2 t squared x squared plus 1. That's what you want to do, right?
Yeah.
Yeah.
Oh, yeah.
That's degree 2. Yeah. No, very good. But that's degree 2. How did I proceed to find an element of degree 2? Yes. So you did. What do you mean? Yes. Yeah, that's right. So now we established that I need an irreducible polynomial of degree 3. How do I find this polynomial? So in degree 2, what's the best? What did I try? Exactly. So here, what do I want to try here? No, but no. Why 14?
Two we did.
No, the question asks find a polynomial of degree 4. Yeah, no. Here I need a polynomial of degree 3. But how do I find a polynomial of degree 3? So I did in in the previous example in F5, I found a polynomial of degree 2 by what did I do? I did the squares. I do the cubes. Now for the square, if you have a not prime, it will always work. For the cube, it will not always work. We'll see now why. In this case, it will work. So in this case, you will be able to find a nice irreducible polynomial of degree 3. The cube trick will allow you to do something nice. So let me write all the elements. One, two, 3, 4, 5, and 6. Now I don't have to fill it all, right? Because these are minus each other. Great. So what's 0 cube is 0. What's 1 cube? 1. What's 2 cube? 2 cube is 8, which is 1. 3 cube is 27, which is 6. 4 is minus 6, which is 1, right? 4 cube is minus 6, which is 1. 5 is minus 1, which is 6. So 5 is minus 2, so this is 6. 6 is minus 1, so this is 6, right? In this case,
Can you explain again why you did cube?
because I want the polynomial of the form, I want to try to find a polynomial of the form x cubed minus something, where this something is not a cube. Just like I did for squares, but I do for a cube.
Because it's 7?
Because 7 to the 3. I didn't put it on
okay.
degree 3. Now, this technique might not always work. In that case, it's nice. It will work. I'm sure that it will work. In general, it might not work. Let's try something else. Yeah. You have to try. I mean, I did this yesterday with F2, for example. Right? F2 of x. I did that last time, right? I took x cubed plus x plus 1. X cubed plus, yeah, you have to try. Yeah.
Did you do 5 and 6 again?
5 and 6. 5 is minus 2, right? So 5 cubed is minus 2 cubed. So it's minus 1. Right? Yep.
If we just
You have to show it's irreducible. Yeah. Yeah. Yeah, but I can give you a one that is a bit hard. I can give you a big number. I can give you F11, for example. Guessing like, well, you have to check the roots. Yeah. If you do that, then yeah.
Without a calculator, needs it. But who knows 4 to the power of 11?
4 to the power 11. Why do you need 4 to the power 11?
Like you just said, if you did a hard one. 11.
Well, I mean, I'll give you something of degree 2 or degree 3. So you just have to know 4 to the cube, for example.
But when does this not work?
So this will work if p minus 1 is divisible by 3. This technique will work. So it's 7 minus 1 is divisible by 3. So you will have an element that is not a cube. Now, if p minus 1 is not divisible by 3, then this technique. Okay. So let's pick an irreducible polynomial of degree 2. What do you want? Choose your favorite. X cubed minus 2. X cubed minus 2. It's irreducible since it has degree 3 and has no roots in F7. Okay. Great. So what is a field of 7 cube elements? Anyone? Anyone? A field with 7 cube elements?
Just x7 x mod x cubed minus 3.
Yeah, exactly. Very good. So F7 of x mod x cubed minus 2 is a field 7 cube elements. Great. Now 2. Show that t squared plus 1 is irreducible So for part B, can you say any non-zero element to any power will not be zero? I don't understand. I don't understand this one. Yeah, Theodore, yes, that's right. That's what you did. Thank you. Great. So now show that t squared plus 1 is irreducible in k of t. I mean, what do I have to do here, really? I have 7 cube elements. 49 times 7, what is that? It's 2. No, it's 50 times 7 is 350, right? So 49, no, wait, what? Well, that's 7 cubed times, let's see, 7 squared times 7. This is 243, right? 243 or 343? 343, yeah. 343. So I have to check 343 elements. I square them, and I see that I get something different than -1. Okay? So it's a big calculation. So every single one of them, you should try them. Of course not. You should not do that. Okay? Of course, you should not take 343 elements and square them and check they're not equal to -1. That's not how to go about it. How do we check this question? Yeah. Yeah. In F7. It doesn't have roots in F7. Doesn't mean it has no roots in K. But it's close. Close. Very close. Very close. That's the way to go about that. Yeah.
Isn't K F7?
No. K is F7 mod x cubed minus 2. So how do you show that this t squared plus 1 business is irreducible in F7? How do you show this? How do you yeah? How do you show it? How do you show it? Yeah. Yes. Yes. Yeah. But how? Yeah, but how? Sure. Sure. Okay. Fermat's little theorem. I want something more general than Fermat. Can do it with something more general than Fermat. Yes. Yes. It says that 7 cube elements, but for the final it would work. What is it? What would work? So how do you prove that t squared? So if you have t squared equal plus 1 is equal to 0, suppose you have a root. What is t squared? What is t squared equal to? -1. What is the order of t in that case? In the so t is non-zero clearly, right? What is the order of t if t squared is -1? 4. So if this polynomial has a root, let's call it a, then you have an element, a non-zero element satisfying a squared equal -1. Right? If a is a root of t squared plus 1, you have an element of k such that a squared is equal to -1. And this a is non-zero. So a belongs to the multiplicative group of k, to the groups of unit of k. If a squared is -1, what is the order of a? If a squared is -1, what is the order of a? 4. Now, can a group of order 7 cubed minus 1 have an element of order 4? Is 7 cubed minus 1 divisible by 4? No. Yeah.
How do we know the order of a squared?
The order of a is 4. So a squared is -1. What is a to the 4? Square both sides.
Oh, okay.
4.
Yeah.
So a has order dividing 4. So a has either order 1, 2, or 4. A clearly can't be 1 because a squared is not 1. And a squared is not
Yeah.
exactly. So a has order 4. Now the 7 cubed minus 1 is 7 cubed minus 1 divisible by 4. What happens? 7 cubed minus 1 is divisible by 4. 7 is congruent to -1 mod 4, right? Yeah. So 7 cubed is congruent to -1 cubed mod 4, which is -1. So 7 cubed -1 is congruent to -1 mod 4, which is congruent to 2 mod 4. So 7 cubed -1 is not divisible by 4. Okay. That's a fair question. That's a very fair question.
You mean 1 mod 4?
7 cubed -1 is not congruent to 0 mod 4. So 7 cubed is not congruent to 1 mod 4. Yeah. Yeah.
I'm not understanding from the 7 cube is congruent to -1 cube mod 4 to the,
Here?
Yeah.
Subtract 1 from both sides. -1 cubed
Oh.
is -1. Subtract 1 from here, subtract 1 from here. So you have -2 mod 4, which is 2 mod 4. Okay, let's write this down. 2. Suppose a in k is a root of t squared plus 1 in k of t. Then a squared is equal to -1. Right? Hence, a is different than 0. Therefore, a belongs to k star, which is k minus 0. Group of units of k, since k is a field, right? Agree or not? Can a be 0 if a squared is -1? 0 squared is equal to 0. So if a squared is -1, then a is non-zero. Great. So group of units of k, since k is a field. Great. If a squared is equal, yeah, no, that's good. If a squared is equal to -1, what is the order of a in k star? Then a4 is equal to 1. Then a has order dividing 4 in k star. Now a is different than 1, since a squared is different than 1. Right? And 1 is different than -1 here, right? We agree? Mod 7, 1 and -1 are not equal. A is different than 1, so a squared is different than 1. A squared equal -1. So a different than 1. So a doesn't have order 2. So what's the order of a? 4. So a has order 4. Now, yes,
How did you know that a squared equals -1, like in the first place?
if a is a root of t squared plus 1, then a squared plus 1 is 0. Right? If a is a solution to a squared plus 1, if a is a root of a t squared plus 1, what does a root mean? It solves. When you plug it in, what you get? 0. So a squared plus 1 is 0. This means that a squared is equal to? Very good. Is that clear?
Yeah.
Okay. So a has order 4 in k star. So this means that 4 divides k star. So the size of 4. So 4 divides the size of k star. And you can do it by the congruence business, or you can say that k star is 342, right? That's 342. Does 4 divide 342? No, doesn't divide 342. Okay? Yes.
Is it essential to say that A is an element of K star first and then like?
Yes. Yeah, because you need to apply the element of the group. I mean, it's obvious. It's obvious that A is non-zero, but it's not bad to say it.
But does A also has order 4 in K?
No.
No.
Well, what do you mean order 4 in K? Additively?
Right. Okay.
Okay,
Yeah.
that's okay. So contradiction. So t squared plus 1 has no roots in K. Since K has degree 2, and since t squared plus 1 has degree 2, in the field, okay, since t squared plus 1 has degree 2, it's irreducible in K of t. Okay, can I erase here? Can I erase here? Or can I erase the question? Which one should I erase or any? I keep the question, okay. Yeah, okay. So if K is irreducible in degree in K of t, how do I construct a field with 7 to the 6 elements? K is 7 cubed. And I have a polynomial of degree 2 that is irreducible in K of t. How do, yeah? Exactly. Thank you. Is a field with cardinality of K to the square 7 cubed square is 7 to the 6. That could be a question. Something like that could be a question. You can expect a question like that, and a nice question like the one we did before, the t24 minus 1, the t25 minus t, something like that. Yeah. These are nice computational questions. Yes.
Remember back then you said 7 is congruent to -1, 1, 4.
Yeah. I'll just proving it. 4 doesn't divide 7 cubed minus 1. Okay.
Isn't 7 minus 3, 1, 4?
7 is congruent to 3.
Yeah.
Which is -1, 1. 3 is -1, 1, 4. Right? 1, 4. Right?
Yeah.
Right? So 7 is congruent to 3, which is congruent to -1, 1, 4. Okay? Is that clear? And then you cube them, and then you see that 7 cubed minus 1 is not divisible by like. Okay? Great. Now that's a perfect question. That could be a perfect question. All of these part B parts, the part B in the first question, the part B, find the inverse of x plus x4 plus x plus 1. Things like that are perfect question on your finals. Where did 342 come from? Oh, it's 343 minus 1, right? K star is 7 cubed minus 1. Right? Is that good? Everybody, are we good? Are we good with this? These are perfect questions. Very nice. Testing that you were here. Now, I don't know if I do the last one, or I could take your question if you have questions. Yeah.
Some questions that are like.
Are involved.
Yeah.
Yeah, there are, but I don't have the practice one. If someone has it, then I'm
Like the p minus one factorial congruent to something.
Oh, okay, yeah, sure. Oh, thank you, I have it. So let's see, let's start doing this. Okay, okay, yeah, that's this question, okay. Oh, well, these are good questions. Yeah, that 125 element, that must be some. Yeah, okay. So should we do them? Should we do them like just verbally? Let's do the first one verbally. Construct a field with 4 elements. How do we do this? Should I write them down, or we can do them verbally? Exercise 0. Should we do them verbally? Should I write it down, or we do them verbally? Exercise 0. Let's do that.
The p minus one would be.
Yeah, sure. I'll just do exercise 0 because it's important. Okay. So construct a field with 4 elements. How do I start that? Guys, in the back. Yeah. So how do I start that? Construct a field with 4 elements. How do I start that? Exactly. How many ones do you have? You have only one, which is x squared plus x plus 1. Okay, great. Now, a field with 8 elements. An irreducible polynomial of degree 3 in what field? In F2, well, in F2 of x. F2 of x is not a field, in F2 of x. Okay, how do I find an irreducible polynomial of degree 3 in F2 of x? What is the criterion that I need to check? No roots, because it has degree 3. It's equivalent of being irreducible. Great. Now, a field with 25 elements. How do I do that? An degree 2 polynomial that is irreducible. How do I find that? What's a good way of finding that? No roots. And how do I find that? The squares. I take the element and I square them, and I try to find an element that's not a square. Very good. A field with 103 squared elements. How do I do that? Yeah, but in F103. So are you going to write 51 squares? Yeah, so yeah, I would say, yeah. Would you want to say something?
Well, x squared plus 1.
Exactly. So 103 is a prime number congruent to 3 mod 4. So x squared plus 1 is irreducible in F103 of x. So F103 of x modulo x squared plus 1 is a field with 103 squared element. Very good. Now a field with 27 elements. I mean, we did that. So what do we need? A field with 27 elements. That is the degree 3 polynomial must be here irreducible. Very good. So how do I check it's irreducible? I try the cubes here. Okay. We try the cubes, it will work in that case. You will find an element that is not a cube. Okay, now a field with 125 elements. How do you do that? 5 to the 3. You start with f5 of x, and then you find a polynomial of degree 3 in f5 of x that's irreducible. And then what do you do? How do you check that? How do you find that? How do you find a polynomial of degree 3 that is irreducible?
Sure. You
You find it has no root. You show it has no roots. Now, in this case, the cube method will not work. Once you cube them, you will get all the elements are cubed. So x cubed minus something will not work. What you do is try something else. You just try to find one that is irreducible. Okay? It's not the end of the word, but you. Okay? Great. Awesome.
Could you explain the one of them?
Yes. Should I write down? Yeah. Now, if you have if P is congruent to 3 mod 4, it's the same argument as this one. Really, P is congruent to 3 mod 4. Okay? Take the polynomial x squared plus 1 in FP of x. Okay? You've seen in the midterm that this polynomial has no roots in FP. It has no solution. X squared plus 1 equals 0 has no solution. This means that this polynomial has no roots in FP. So this means that fp of x, since it has degree 2 and it has no roots,
Oh, and then.
this means irreducible. So this one is a field with p squared elements. If p is congruent to 3, 1, 4. Okay? Yep.
Would it be enough to say, we know that
No,
x
you have to
squared
justify.
is congruent to one minus one?
Justify it. Just don't use it. Especially if that's the question. Okay, if you need it in a sub question, use it. But if that's the question, construct a field of 3 elements, just write down a bit.
Like explain that.
Yeah,
x squared
exactly.
is congruent to minus one mod p. No solution,
Yeah.
like redo the.
I mean, I'll be here. If I have to ask you this, the first step will be show that x squared minus 1 has equal minus 1 has no. And then construct a field with p squared elements, p congruent to 3. Okay, great. Is that clear? And it's congruent to 3. Then you can use that. Congruent to 3 with 4. Okay, great. No problem. Okay, great. So okay, now let's move on to the p minus 1 question. Shouldn't be bad. Did I say p should be, well, p doesn't matter, but let's assume p is a not prime. Okay, doesn't, if p is 2, it's obvious, right? In that question, if p is 2, then the result is obvious, right? 2 minus 1 factorial is minus 1, which is 1. Great. Doesn't matter. So let's assume that p is a not prime. Suppose p is a not prime. In fp of x. And let R. Okay, and to show that p minus 1 factorial, oh, p is prime. Here, p is a not prime. In that case, p is a not prime. Okay, how do we do the first one? The first one is not bad, right? The first one, how many roots does a to the p minus x to the p minus 1 have? All the non-zero elements are roots, right? By Fermat's theorem. You see that or not? By Fermat's theorem, by FLT, a belongs to fp star, and a to the p minus 1 is equal to 1. Agree or not? Fermat's theorem. So this says that any a in fp is a root, any non-zero a in fp is a root of x to the p minus 1 minus 1. Yes? So any non-zero a hence, how can you factor this one? Is 0 a root of this one? Is 0 a root of this polynomial? Plug in 0 minus 1 is a root of what? I mean, of x to the p minus 1. And is 0 a root of this polynomial? Is 0 a root of this polynomial? 0 is not a root. since 0 minus 1 is different than 0. Okay, so how many roots does x to the p minus 1 have? If all the non-zero elements, p minus 1 roots. And each one of these will divide xp minus 1 minus 1. Right? So just by factoring it, so x to the p minus 1. Just the product of the non-zero of x minus the non-zero linear, the non-zero elements. That's it. Now, how do you prove part B? P minus, is that clear? How do you prove part B? Part B, just plug in 0 on both sides. Part B, where x equals 0. What do you get on this side? Minus 1. What do you get on this side? Minus 1. Was minus 2. Times minus to the p minus 1. So you get minus 1 is congruent. So how many minus 1s do you have? You have minus 1 times p minus 1 times p minus times 1 times 2 times p minus 1. So you get minus 1 is congruent. Well, if p is odd, then minus 1 to the p minus 1 is 1, right? This is 1. Then p minus 1 factorial. Thanks. Okay. That's a nice question. Okay. Questions? Next question. For Friday?
We will have a question.
Pardon me? Yeah, something nice. Nice calculations. Yeah, but those are direct consequences. This is Lagrange. This is not a ring, right? This has nothing to do with. This really has nothing to do with before. This has nothing to do with what we did now. This is really Lagrange's theorem, right? This is literally Lagrange's theorem. A to the p minus 1 is equal, just like the one with t to the 24 minus 1. Did you ever need that it's a ring of polynomials of I don't know what? No. You just need that it's a field with 25 elements. So the non-zero elements form a group of size 24, and then you apply Lagrange's theorem. But really, you don't have any polynomials inside. So this is really pre-mature material. It's not like post-mature material.
I still don't see why at all.
Here. Any non-zero A to the order of p minus 1 equal to 1. Or Fermat's theorem, which follows from Lagrange. How do we prove Fermat's theorem? By Lagrange. Right?
For me, that was like the subgroup is the order.
Oh, the order of the subgroup
Yeah.
divides the order of the group. So the order of the subgroup generated by A divides p minus 1. The order of the subgroup generated by A is the order of A. So the order of A divides p minus 1. Right? This is Lagrange. This is how we prove this one. So G to the order of G is equal to G to the order of the group is the identity. Right?
Yeah.
That's it.
Is
G to the order of the group, G to the number of elements in G if G is finite is the identity. That's it. Really, you have no polynomials or anything here. X dot dot dot, it's x minus p minus 1 at the end. Okay? These are very, I could also elaborate on this, but yeah, things like that I can elaborate on. For example, I can ask you with this, show that x squared plus 1, if p is congruent to 2 mod, if p is congruent to 1 mod 4, show that x squared plus 1 has 2 distinct roots. So if p is congruent to 3 mod 4, x squared plus 1 has no roots. Then if p is congruent to 1 mod 4, using this, you can find 2 distinct roots. They are p minus 1 over 2 factorial. Squared is congruent to minus 1. Using this, if p is congruent to 1 mod 4. These are very nice questions. Yeah. So if p is congruent to 1 mod 4, the x squared plus 1 thing will not work. X squared plus 1 will not be irreducible in FP. If p is congruent to 3 mod 4, then x squared plus 1 will be irreducible in FP. And if p is 2, then it's reducible. So yeah, things like that. These are very nice. It has nothing to do with the polynomials. Just at the end, it's irreducible. So, boom. Yeah.
Sorry, does that say phi?
Where?
Minus 1 congruent to minus 1, or p minus 1 phi 2.
Oh no, this is there was a 0 there from previous. It was 1.
Oh.
1. I just factored a minus 1 for every single one. Do you mind turning the camera towards the right board? This one, like that? Like that? Is that better? Now I'm at the extreme. I cannot do it any further. Yeah, I cannot do it any further. Let's see if I can do it more. Yeah, but that's it. Okay, so these are perfect questions. These are perfect questions.
For brains?
For brain part, yeah. For the calculation one, yeah, they're perfect questions. All of these are nice questions. There's nothing that takes more than 10 minutes. It could be two parts, for example. The first part could be like show that I don't know, find a field with 25 elements. Part B, solve t to the 24, find how many roots t to the 24 minus 1 has in that field. This is part A, part B. Pardon me?
They'd be like
Yes. They'll be linked. Yes. Yeah. Yes. Those are equivalent. Factor t to the 24 minus 1 and k. How do you any non-zero element is a root, right? So what is this? This is just phi the product as A. A is different than 0. It's minus A. Yes. No, but let's not say that. Let's not say that. Let's say we'll go and kill this tomorrow. Right? T to the 24 minus 1 given field. You just factor the non-zero elements. Right? Any non-zero element is a root. So any x minus non-zero element is a factor of this thing here. Great. Now, this is a field with p elements. So p minus 1 is the group, is the order of the multiplicative group, right? So x to the p minus 1 minus 1, any non-zero element is a root of this one. It's the same idea. I'm just asking you, show that every non-zero element is a root and factor this. Same idea. Okay? Same idea. This and this are equivalent. They are, yeah, not equivalent, but it's the same idea. So you're looking at the multiplicative group of k, which has 24 elements, and you're showing that any non-zero element is a root. So the product is t here. The product, so t to the 24 minus 1, you factor it. No, it's the same. It's really the same idea. Yes.
And this, the p minus 1 of the 2 factorial squared.
That's a more an arithmetic exercise. It's nothing to do with polynomials. It has nothing to do with polynomials. It has nothing to do with polynomials. Yeah. Start with p minus 1 factorial. If t is congruent to 1 mod 4, this is 1 plus 4. So this is 4m factorial, right? So if t is congruent to 1 mod 4, so you can write p is 1 plus 4m, right? Okay, this is then t minus 1, 4m factorial. It's congruent to minus 1 mod t, right? And then p minus 1 over 2 is 2m factorial. So it's 2m factorial. And then write down 2m plus 1 up to 2m plus 2m. Okay, I'll leave it to you to check it. You know, I don't want to spoil it. Okay. I'm not saying it's going to be on the final, but you can just continue. No, I don't want to spoil it because we're going to use it tomorrow. Tomorrow, where is you not on the final? Well, it's a calculation content, so it's something that you have seen before. It's something that it's basic stuff. Tomorrow we'll do quadratic reciprocity. That's not going to be on the final. But this is like the perfect. I'll do it another way. I'll not do it this way. I'll do it another way. I'll do it. I might do it using this immediately.
But we can use the methods done tomorrow.
Yes, definitely. Yeah, definitely.
We don't need to prove it, but we need to know how to use them for.
No, even I mean the proofs that we're going to do tomorrow, the calculations we're going to do tomorrow are basic calculations, are basic congruence calculations. Okay, they don't have to do anything with polynomials. Nothing. Zero. Yeah, so I mean, again, it's going to be fair. You'll see on Friday. It's going to be very fair. Honestly. I compared everything. I compared every single problem. The homework should be fine. If you study. If you didn't study, then you will see nothing. You know. I can tell you. But if you studied, then it's going to be fine. So if you give it to someone who didn't take that class, I can guarantee it's going to go hard. But if you took that class and you studied and you did your homework, it should be fine. And I told you the homework are really good. I told you the median of the homework is 100. So like more than half the people got 100 on the homework. I don't think you have this in any other classes. You don't have the median equal 100 in any other classes. In this class, the median is 100 on the homework. Yeah.
So would you give us a hint, like?
I will give you the final hints. Yeah.
Like, for like.
Yeah.
Okay.
Yeah.
I would have.
I think in the final I have 3 hints to my memory. 3 hints. 4? Okay, so 4 or 3. It doesn't. I mean, if there are 7 questions, I don't think I've put 4, right? So there might be 3 hints. I think that there are 3 hints, and 3 hints makes the problem very easy. Yeah.
Can you explain the step from 4m factorial?
Yeah, just I'll do this tomorrow. So write this 2m factorial, and then write this as 2m plus 1 until 2m plus 2m. Right?
That is the same as 4m factorial is congruent to minus 1.
Yeah, and then that thing here, I don't want to spoil it for you. I don't want to spoil it. We'll see that tomorrow. Okay, we'll see that tomorrow. We might see it another way. But again, try it. It's just a congruence exercise. It's a congruence exercise. Try it. It's not very bad. But again, I feel it's gonna go well for the people who study. You will see tomorrow. Actually, not tomorrow. Why? You will see on Friday. You will see on Friday. It's gonna go well. Trust me. If you study, you know every single homework, every single theorem, every single exercise. Yeah, but I mean, I tell you, 55 on 70. there are some things like repeats of homework and exercise and notes. That's a fair deal, right?
Yeah, but there's.
Yeah, but you have 55 on 70
Wait, 55 out of 70s come out.
from homework, notes. I said this many times. So like,
You could understand nothing is impossible.
no, but if I switch something, for example, then you'll be confused, right? If you just memorize without understanding, and I switch one thing, okay. So again, you should have a good grasp of the material and know how to do the exercises. Then you'll be fine. I'm personally not very like. So I know like last year's it hasn't gone well. This year it will be better. Yeah, I'm pretty sure. And this year is much harder. It will be better, and this year is harder. But I can tell you it will be better. Pardon me?
You're gonna promote.
No. But I'm saying it will be better. It will be like I know from the level of the class it will be better. I know. Pardon me?
Yeah.
I changed last year, yeah. But no, I know from the level of the class. This class is very strong. It's a very strong. Now you might not expect that, but I see the grades. It's a very, very strong. Median is 100 on the homework. It's a very strong group. Median is 100. You don't get that in your. You don't. I mean, my computer science homework were like 70, 60. I never got like more than 90 on a computer science homework. No, but like, I mean, like, no, it's no, I mean, and it's on Friday. I'm personally not 55 points. I'm not worried about. There are 15 points I'm worried about on 70. Not all of these are hard. You have 5 that are easy, 5 that are medium, and 5 that are slightly more than medium. It's not like there is nothing unreasonable. And if you're the 55 points, say, if you studied and if you know everything, you should be done in an hour. I mean, the whole thing, yeah. I mean, let's say the 55 to be more conservative. If you know everything, you will be able to read everything and say, okay, I know this, I know this, I know this. Oh, that I have seen, that I have seen, that I have seen, that I know how to do. So yeah. No, it's not. It's not. You have to be more creative. Just things that you haven't seen. Some of them are very easy, and some of them are medium, and some of them are slightly harder. But it's not. You don't have to be very creative. It's 5, 5, 5. So 5 is supposed to be very easy. 5 is supposed to be medium, and 5 is supposed to be slightly more than medium. But there's nothing really hard in that. Yeah.
You know the 4 group actions that we've seen in class.
What are they?
Well, that was that's my question.
So what is the first question? We saw G acting the symmetric group acting on the set, right? Sim S acting on S. That's the very first action. Then we saw G acting on the cosets. Then we saw G acting on G by conjugation. Then we saw G acting on a normal subgroup by conjugation. And then we saw G acting on a set of the conjugates of a subgroup. And then the restriction of these actions to subgroups. So I think these are the ones you have seen in class.
So as in like the ones that in a question where they don't give you the group action where you have to come up with it.
No, you won't have to come up with any group. Yeah, I mean unless it's a I mean, for example, if I ask you find the surjective homomorphism from S4 to S3. That for example, the first question could be find all the subgroups of order 8 in S4. Yeah, exactly. So that for example, if I were to give that, I won't give you many hints. I'll just give you find the subgroups of order 8 in S4. Then use your work to find blah blah blah. Then or if I have to give you a group action, A and B are almost always related. Okay, if you have 2 parts A and B, then they're related. That's no question. Okay, I won't give you A and B that are not related. So for example, if I give you a group action, so first of all, so if I tell you show that G acts on G by conjugate, I'll give you a practice midterm. I'll release it tonight. The practice final, sorry. So for example, there is one question. Show that G acts on G by conjugation. and the set of fixed point is ZG. Okay? That's part A. Part B, show that if G is a P group, then ZG has an element of order P. You will have to use the previous part, even if I don't tell you. Okay, so whenever you have A and B, then they're related. Okay? So, and whenever you need an action, I will most likely give it to you. Or if I don't give it to you, you can do it with an action, but there is some other way to do it. Okay, so yeah.
And will you be like looking over to find like once TAs have marked them? Will you like have like a quick scan and be like, yeah, that was good, that was good? Or you just like leave it to TA?
No, usually we have a quick look. Usually we have a quick look. Usually we're very careful. Yes.
Because it just feels like there's like a lot of ways to do like questions.
Yeah. No, but that you shouldn't be worried about. Okay, that you shouldn't be worried. That's the grading is the last thing you should worry about. I mean, the TAs we tried to not to remove a lot of marks the midterm for things. So, and this, yeah, in the midterm we realize sometimes if you made a mistake, for example, in the Euclidean algorithm, some people made a small mistake. We then decided to just dot 1 mark, for example, if it's a small mistake. Okay, we didn't dot like 5 or 10 marks. We try to be very reasonable in the way we grade. We know you're under a lot of stress, so that's not we don't want to add to this. So grading is going to be lenient but fair. If you write something that is not good, you will get 0. Okay, if you just state theorems, if you write theorems that have nothing to do, you will get 0. But if you write something and you show us that you understand, okay, for example, construct a field with 7 cube elements, and you tell me, okay, start with F7 and get an irreducible polynomial of degree 3 in F7, and I check that this polynomial is irreducible, it has no roots since it has degree 3. On 5, that can give you 2.5, 2 or 3 marks.
Just by writing down what you just said.
By just writing down this. Exactly. This shows me that you understand what you're doing.
And then you have to compute it to get the rest of it.
Exactly. You have to find it. But that shows me that you understand. Okay, that if you show me that you understand, then you will get some marks. But again, my personal view I'm not worried for this group. In general, like the grades are very good. Like they're really good. 100 median on homework is really high. That's not counting the bonus. That's not counting the bonus. I didn't grade the bonus yet. But I mean, some of you. So if someone got 100 on this midterm and got 100 on the homework, they need 70% on the final to get an A in the course. That's not a lot, right? It's usually you're expected to do better than 70% to get an A in the course, right? Yeah. So yeah.
Yeah, like our or is it already?
It's all the homeworks are graded already. Everything is released, no? I released everything but the bonus. I didn't do the calculation. I'll do the calculation like just at the end when I compile everything. But again, it's I'm not worried. Personally, I might be wrong. I mean, I was worried for the midterm, but it turns out that I shouldn't have been. But here I'm personally not worried because I know you studied the homework, you studied the proofs from the notes. If you did that, you should be fine. If you didn't do that, you won't be fine. That's the equation.
When you say study the proofs, you mean learn them by heart?
Learn them by heart, know how to write them. No, know how to write them, know how to derive them. Exactly. So this is the way. Again, no, seriously, it's okay. So let's see. Would you say that 57 difficulty is the same on the midterm? Yes, I would say so. Yeah. By the same, I mean I don't mean the concepts, but the fact that you have seen them in the class or in the homework or in the notes or in the practice sheets, things like that. So these 2 practice sheets, count them as a homework that you have to revise. Okay? And again, for the practice sheet, don't just look at them and rewatch the recording without just rewatch. Don't do that. Rewrite them. Make sure you know how to do them. Rewrite them. Rewrite every single step. Now, every single step. Now, try to do it without the recording after. Now, I'm assuming that you have nothing but me in your studying, but I mean, it's Friday. It's the first exam. So, like,
Yeah, that all makes it bad.
no, I
Okay,
mean,
first exam.
no, I mean, yeah, it's the first exam, and then you're done. You study for it. You put all your energy in it, and then you see what happens after. No, isn't that the way you do?
Yeah.
Maybe. Yeah. Exactly. Okay, so any questions about the course, the material? I have office hours now. Do you guys have questions about the material or not?
Say how many groups between like Z1 15Z and Z1 40 or whatever. Can I know I can't just state it's G's and B's as the 2. Can I prove that and then just say, oh, because I've proved that?
No, I mean I will be clear on what to expect. I'll be clear.
Okay.
I'll be clear.
But like if I wanted to approach the question that way, I just memorize that proof and then
Yeah, sure. Sure.
prove it and then apply it to the.
Again, there will be no long proofs. There's nothing that's going to be very long. Yeah. You won't need it. You won't need it. Okay.
Use it either.
You won't need to use it either. You can't use it. To my memory, you can't use it. Yeah. Yeah. Tomorrow I have a session. So tomorrow I have one. Yeah, I'll finish them. Yep. Yeah. No. Unless I tell you in part. If you need to do that, I will tell you in part A. Show that G acts on G mod H. Yeah, show that this is an action. You have to do it. Part B. Show that the action induces a morphism. Blah 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 blah. Whose kernel is that? Yeah. Yeah. So, but yeah. So again, just do the home. Have you been doing 7, 8, 9?
You did that actually. 6 on the side. 7, 8.
Oh, yeah. Something here like this.
Yeah.
But then you just say,
Yeah. And now I know how. I need to study that.
Yeah, 7, 8, 9 are very important. Yeah. Okay, so anybody has questions? I'll just take questions from people attending. Let's see. How many of the proofs are directly taken from the notes? So 3 proofs will be taken directly from the notes. And no, all the exercises are of equal marks, but they're not of equal difficulty. Okay. No, the 3 proofs. Okay. If you can ask for just those one. Just how many people? Okay, maybe let me take the question from the people online first. Okay, so would the proof come as sub questions of larger problems? Could be, or could not be. Okay, but the first 3 proofs are just questions. But then homework assignments, you could see them in subparts. I don't think I've put one that is directly. I don't think I've put one that is exactly the same, but pretty close. I'd say it's pretty close. Exactly the same or very close. Sure, take it this. Take it down. You will have one question. Not every question. Exactly. Yeah.
First 3 or 5.
I mean, don't count.
Oh, right.
Don't count. Study. And don't say, okay, this. and I need to this. I need this many to get an A. I need this many to get a B. I need this many to get a C. Don't do that. Just study, and then do it this way. It's better, I think.
How many prefixes are going to be from groups?
From groups. So in the first three questions, you will have one proof from the nodes that is from groups. So the first three questions, the first one is on groups, taken from the group parts, post midterm, and the next two are taken from the rings parts. Then third, then four and fifth are like questions on groups, I think. 6 and 7, one is on groups and one is calculation on rings. Calculation on ring is things we did today, and like we covered like Friday, and like the examples we covered yesterday. You will have no proofs on ring groups and rings. Yeah, but for example, you can have a homomorphism question on groups. Okay, so but I won't ask you to prove the first isomorphism theorem. I won't ask you to do that.
Not for the silenced. Or you have to.
CeLO 2, CeLO 3, you have to know the proofs. Yes, yes.
For
Yeah.
CeLO 3, there's part where it says by the previous proposition.
Yeah,
Do
so
we prove that?
no, so I will tell you if I put CeLO's third theorem, I will tell you state CeLO's second and third theorem. For example, you could state them and then prove the third theorem. Note, you may assume the second theorem. Okay, but I will not give you the state.
But also
Oh,
the
yeah.
proposition that the index of the normalizer is equal to the.
Number of conjugates of H of P. Yeah, that you need to prove. Or I can tell you assume it. Okay, or I can tell you the previous part, for example.
But it'll be clear if we have to, like, if, unless you say assume it.
Yeah, but I'll be clear.
So we can just say, and by the whatever.
In what?
We don't have like inside of that theorem, the population, like just mention.
No. Usually I'll be clear. Part A will be that, for example.
You said no long proofs inside of that theorem is like 2 pages.
No, but I can break it down, right? I can break down 2 exercises.
Oh,
So like the exercise G acting on yeah, no, exactly. I mean, and these are not dependent on each other. Or I can tell you, you can assume this. You can assume this. You can assume the following fact. This is fine. Again, and again, I give you 1 page. I don't give you like every single thing is fit on a page like this. So the question, let's say, is this long at most, exercise 1, for example, and then you have the rest. Me? Yeah. Here.
That just gets really small.
Yeah, but I write pretty small. So like again, it shouldn't be long. It shouldn't be long, actually. Okay, so let me take people that are online so that we can. Yeah, so a few moments someone mentioned something and you said we don't need it. We could not hear it through the audio. Could you please repeat that part? Calculators, maybe? Is that?
No.
Okay. Calculator. Oh, calculators, no. Oh, okay. Oh, fundamental theorem of finitely generated abelian groups. That we don't need. Do we need to know that as first as more theorem for rings? Yes, you need to know it, but I won't ask you to prove it. What lectures should we focus on more importantly? Like where to start or the cutoff? Now, I've said this many times, right? Post midterm is the key. I've said this like 3 weeks ago, maybe. Like post break, post fall break, yeah, post reading week. I've said this like 3 weeks ago. Else, people attending online, please ask your questions so that the people here can ask. Or you prefer to listen? You guys prefer to listen? Yeah. Okay. No, just you. Yeah, I don't want you to do that. People online, please ask your questions. If you guys need to ask questions, I will take them. Oh, you can't hear them when they ask. Okay. Maybe. So if you can ask, maybe can you stand next to the computer without showing up on the camera? If you could do that. But if you want to do that, you don't want to do that? No, that's okay. That's okay. If you don't want to, then you can ask later. That's okay. Okay, so great. I will shut the recording. Do you guys have questions or not? Any more people attending online? Okay, anyone has questions on the exam? Maybe just repeat what they're asked. Okay, I'll try. Can the recording stay so that we hear? Yeah, sure, you could do that. So we can know the answer too. Yes. Okay. Great. Yeah. Okay. Questions? So the proofs for rings are done in lectures. Yes, I've said that like 600 times for now. One proof was from Monday. So it's one proof was from the first Monday to the first Monday to the next Monday, and the first for lecture, and one proof is on characteristic. Yeah. Is that did you guys hear this? So there's going to be a proof from the characteristic part, and there's going to be a proof from the first for lectures on rings. First for lectures from Monday to Monday. Yeah.
Last one question. You said, like, you mean like no proof? It's more like how do I say? Like those questions were like, say like write this like order 8, like subgroup of order 8.
For example, that could be a question. Or show that G acts on G by conjugate. So it's more application of the theorems.
So like
Exactly.
we need to know how to do.
Exactly. So exactly. For example, show that G acts on G by conjugation. Now you can consider this to be a proof, but this is more like a calculation. Okay? Yeah, things like that. I won't ask you like the notes really are the first 3 questions. Now, for example, write down a subgroup of order 8 in S4. That could be a question, but that's not a proof, right?
Or like theoretical rings is like the polynomial.
Exactly. So things like we did today. Rings like things like we did today. Exactly. Yeah. So did you guys hear this online? So like the first 3 questions are going to be the proofs from the notes. I think everything else, like, I mean, could be from the notes or could be from the homework, but these are more application of the theorems. They're not like the theorems themselves. I mean, it could be a theorem, but it's a small theorem. You see what I mean? A small proposition. But I mean, theorems could be proposition as well. From the notes, like it's not the big theorems. It could be propositions as well.
Serum proposition and like proof question, because like technically when you do proof of a proposition or serum, technically you're proving.
Exactly.
You are like, it's like proof question.
Yeah, but but it's more like homework type question. Okay, for example, how I divide the question. There are 7 questions, all are worth 10 marks. The first 3 are exactly from the notes. The first one is on groups. The second one is on the next one is on groups. Now, in the remaining one, you have one calculation question on rings, like the things we did today and things we did, examples like, polynomials and things like that. And then you have group actions, questions mostly on group actions, calculations, things like that. Yeah, questions, yes. If you could come complete, just
This is the questions today, and I just want to know like whether I'm right this correctly. Is it the p times the
P is
size?
equal. P equal.
Yeah. Oh, so I got it. Yeah. Right.
P is equal to 0. Okay.
So I want to know like whether since it is 24 elements, it is like because K is the
25.
Yeah, it is 5 P is equals 5 and M is equals 2. So like it's 25 elements, but we like minus the 0, 1. So it is 24 elements. And like, so if in this case, like if G0 is equals 0, so you got 25. Why? That's oh,
Okay. If G0 is 0, in that case. So take t to the 25 minus t. Like the example we did on times t. Time t to the 24 minus 1 times t. Every non-zero is a root of t to the 24 minus 1, and 0 is a root of t. So you have 25 roots. Sorry, I just answered her. Yeah. So would guys, that's important. Would you be willing to tell us if we need to know the proof of CELO second or third? They're both long. Yeah, they are long, but second is not long. Second, I don't think is long. Third one is a bit long, yes. But you need to know them. Yes, you need to know them. You need to know them.
Let's choose one.
You will see.
Which one? You can split it into more parts.
You can gamble. You know, like you can try to. Yeah, you see. No, it's
Yeah, I forget.
Oh, okay. I know the answer, but I know the answer. I know, yeah, I know both. But yeah, I mean, you have to study them. Again, I reduced the material by a very, very, very fair amount. Pardon me? Yeah, I mean, I reduced it. I was reasonable, I think. I hope I was reasonable, I think, by reducing the material by a fair bit. So can you tell us more about the final? I think I've talked a lot about it. Like it's a I think of yeah, I mean, what do you need to know? No, all the questions are more 10 marks. All the so to my memory, the proof from the notes, you have 3 of them, and the 3 of them are 10 marks, and each is 10 marks. To my memory, just to my memory. I'm not gonna as much as I can. Yeah, that's yeah.
So if we need to like, or
Guys, if you want to ask question, could you like just circle around so that people can hear you?
subgroups from S2 to S3. So is it justifying that we write H equals like
You leave all the subgroups of order 8.
S4 to
Sorry, I'm just how many? Sorry, that's how many questions in total with the sub questions? I don't know. You will see in 3 days. Is the proof question just asking to state the proof, or there is parts A, B type of questions? So it could be the first one, state Celo's second theorem. B, prove Celo's second theorem. Okay, so it could be like that, or it could be state and proof. So it depends how you say parts A and B. But generally, they're related. If there are parts and B, part A is made to make part B easier. Okay. Yes. So if you want the subgroups of order 8 in S4, you write down the symmetries of the square, right? Now, if you want them all of them, you know that there are 3 of them by Celo's third theorem. Now, how you do is that you relabel your square. Instead of having 1, 2, 3, 4, what you do, you do 1, 3, 2, 4.
So it will be three different.
Sorry.
If we need to like write all the subgroups,
Yeah.
so we will have like 3 H like that H1.
Yes.
So just like we change the order.
Attention. So you have what you do for the order. You have 1, 3. Okay. How do you pick the order? You have 1, 3, and then you have 1, 4, and you have 1, 2, and then you choose the other 2 to be they're the same. Okay, so you have 1, 3, then the other 2 are 2, 4. Then you have 1, 4, then the other are 2, 3. You have 1, 2, the other are 3, 4. That's how you do that.
So this 2 views of this 2 doesn't matter.
Yeah, so if you have 4, 2, okay, say you have 4 here and 2 here, you still have 1, 2, 3, 4. It's the same square.
Oh.
It just flipped. Okay.
So we only like it only matters for like this.
The first 2, and then the other.
This, like for 2, but like it's same as this.
Exactly. You see that? Okay, because 1, 2, 3, 4, and then it's here 1, 2, 3, 4. It's the same. If you reflect it, you get the same square. So the square is the same. Exactly. Is the proof? Yeah. So that I answered. Will the questions be similar to our homeworks or notes, or there are some format we've never seen? No, there's gonna be a question that you've never seen. There's gonna be a question that you've never seen the likes of. Yeah. But it's not worth a lot. So I'm gonna surprise you, yeah. But it's not gonna be a bad surprise, you know. Yeah, you will be it's not all book work. Yeah, if that's your question. Yeah, it's not all exactly from the homework or similar to the homework. There's gonna be some things that you know you have not seen. I'll put you on the spot with 2-3 questions. Not big questions, could be parts of questions, yeah. So like 15 points is something that you kind of never solve, but it should be fair. Okay. Yeah.
So says P.
Yeah. If G is a billion.
So it have like it's that G equals
Where?
here. It's normal in G, and so
G mod ZG is a group of order P, right? So if any group of order P is cyclic, right? Take an element that is not the identity. The order must, okay, great. So any group of order P is cyclic. So G mod ZG is cyclic, right? So G is a billion. G mod ZG, yes, because Z mod Z is cyclic. Hence G is a billion. Right? That's the theorem of before. If G is a billion, if G mod ZG is cyclic, then G is a billion. Theorem before. The one before. If G mod ZG is cyclic and the homework 6, then G is a billion. Okay? So if G is a billion, then ZG is equal to G. And that's a contradiction. How many calculation questions? What do you mean calculations? Like the ones we did today? Yes? Is that what? Yes, so you have one question like that. Yeah, one. Exactly one. Three will be on rings and 4 will be on groups. No problem. Yeah. Yeah.
same. They're the same cycle sector. How do we show that?
It's a homework question, so but you don't have to show it. I won't ask you to show it. You don't have to say the results, yeah. You don't have to show it. How do you find the size? How do you find how many elements in the conjugacy class? Yeah, okay, maybe I can write on the board. Okay, guys, that's a nice question. So how do we need to depend on the type and structure. So let's explore. How many cycles? I'll pick a representative. And size of the class. Okay, so first you have a 4 cycle. I mean, you know, that's first.
Oh, is that the table that you? Oh,
Exactly. So how many 4 cycles do you have in a score? You're free to choose the first one. The first one doesn't count. Is it 4 factorial or is it 3 factorial? You can choose.
The first one doesn't count.
Yeah, but that's how many elements in S4 you have. But how many 4 cycles you have? 4. 6. 6. The first one doesn't matter. Okay, once you choose the first one, it doesn't matter. Now the other one, you can permute them and you will get different 4 cycles.
It's like the number of transpositions within that. Sorry.
Well, it depends how you can write them in many ways, right?
Like 1, 2, 3, 4, 2, 1, 3, 4, and then like 1, 2, 4, 3, and then 2, 1, 4, 3.
I can't see it though.
No,
I can't see it though.
how do you see it?
I see it that you can choose the first one.
Yeah.
Doesn't matter to choose. Okay. So any element could be in the first one because you can permute them. Right. This one, for example, you can write as 4, 1, 2, 3. Right. Yeah. So really, it doesn't matter here what you have. And once you have this one fixed, you just permute these three. How many permutations do you have? Or just three treatment for 6?
And after it's like 3 cycles.
Yeah, is that good?
So one is always fixed then. One is always stays in that.
Exactly. But you can still change it. You can change the 4 into 1, right? Shift everything.
Yes.
Yeah.
But that counts as one.
Yes.
Yeah.
So that's why you have 6. You don't have 4 or 5. Or you can say each one here. You have 4 different ways to start it,
Then you have the 2 cycles.
right? 4 factorial divided by 4. You get 3.
Which is
Okay, that's one other way. Okay, great. Then what do you have? You have so what do we have? You have 3 cycles. 1, 2, 3. How many 3 cycles do you have?
3.
Are you sure?
is that the same like you fix one and then you you have one.
Oh, you choose the one that doesn't appear inside.
Mhm.
How many choices do you have for the one that doesn't appear here? 4. 4. Right?
Yeah, okay.
4. Now, once it's fixed, you can start with any one.
And
Then the other 2 you permute them. So it's 4 times 2 factorial, so it's 8. Okay. Now what do you have?
2 cycle?
2 by 2, or just transpositions? Just 1, 2, for example. Okay. So 1, 2. You just choose the 2. Choose the 2. How many ways can you choose 2? So it's 4.
4 times 4.
4 choose 2,
Right.
which is 4.
Yeah.
4 times 3 over 2. 6. Is that right? 6. Yeah.
Interesting.
Why the 4 choose?
You just choose the 2 that don't appear.
And then just above it.
You choose the first one that doesn't appear. You have a 3 cycle. And then for the ones that appear, the first one could be, by the same argument.
And then 2 factorial.
Yeah, exactly. Okay, great. Let's do. What do we have then? We have the 3 type. Yeah. So this one.
Yeah.
Okay. So what do you do here? First, you choose the 2 that appear here, right? Choose the 2 that appear here.
Would it be 4 choose 2? 2 choose 2?
So 4 choose 2, and then the other ones are fixed. Once the 2 that appear here, then the other one are determined already. So it's going to be 4 choose 2, but pay attention. Pay attention. Once you do that, you can permute them. They're disjoint. They commute.
So
So it's 1/2 of 4 choose 2. So what's the end? It's 3. Yeah. Okay. Yeah. And then what do we have left?
okay.
Here, that is it. Yeah, that's it.
So those are like the good
Conjugacy classes in S4.
yeah.
And the definition of the conjugate class is class of all conjugate elements. What's the conjugate element again? I always forget.
It's G x G inverse as G is in G. That's the conjugate. It's the orbit of X under the action of conjugation. If that's better.
So the orbit of X is what G operation X equals X.
No, that's the set of fixed points.
That's
No, sorry, no. That's a singleton. So
Yeah.
it depends. If G belongs to the stabilizer, then G star X is X. Now, if X is a fixed point, means that G star X is equal to X for all G in G.
So it's just set X. But,
So it depends on what you're considering. What are you considering?
it is a subgroup.
So you fix X, and you look at the set G or you look at the possibilities of G such that G star X is X.
So it stabilizes the whole group.
Not necessarily the whole. It stabilizes a subgroup of G.
If singleton orbit is just the
Oh.
whole set of X, then
You mean if the singleton orbit, if orbit of X is equal to X, this means that the stabilizer of X is the whole orbit. That's right. Yes.
Okay.
Is that what you meant? Yeah,
Yeah.
that's right. Yeah.
But then what's the conjugate again? Sorry.
Conjugacy class means that, so you know what the action by conjugation?
X.
G star X is G x G inverse. Conjugacy class is the orbit of X under conjugation. So it's G star X as G ranges in G. So it's G x G inverse as G ranges in G.
But like I get that like theory, but then I just don't understand how it's applied to this. When you say, oh, like conjugate garments of like S4.
Yeah, so in S4, you have a theorem that tells you that two permutations are conjugate if and only if they have the same cycle structure. So any 2-3 cycles are conjugate. So for example, this one and this one belong to the same conjugacy class. This one and this one belong to the same conjugacy class because they have the same cycle structure. This one,
Oh, as in like same number.
yeah, it's same, like it's a product of two by two cycles. Disjoint, when you write them as disjoint cycles, you get the same shape. And that's if and only if.
Very good.
Of S4?
Yeah.
Okay, so how do you find the normal subgroups? You know that the normals, first you need a subgroup, and second you need a union of conjugacy classes. So, or you need a union of conjugacy classes first, and then you need to be a subgroup. Now, what are the possible sizes of subgroups of order 24? This is the divisor of 24. This is how you start first. Great. Now, a subgroup must contain the identity. So you should start with the identity. Great. Now, what are the divisors of 24? 1, 2, 3, 4, 6, 8, 12, 24. Great. Now, if you have a normal subgroup of size 2, do you have any other, you have 1. Do you have any other conjugate class of size 1? No. So you have no normal subgroup of size 2. Of size 3, can you like match? So technically any normal subgroup must be 1 plus something, right? Here. Any normal subgroup must have size at least 4. Because you have 1 plus 3. At least, right? Right. Now 1 plus 3. Take the union of these two conjugacy classes. Does it form a subgroup? It does. Right? So if you take, I'll call it B. B is the identity. 1, 2, 3, 4. 1, 4, 2, 3. 1, 3, 2, 4. Is a normal subgroup. Because it's a subgroup, you can check that if this is A and this is B, then this will be AB and this will be BA. And A and B will have order 2. So you can check that this is a subgroup. And it's normal because it's a union of two conjugacy classes. That's done. Now, of order 8, can you have a subgroup of order 8? Can you add these up 1 plus something to get 8? No. Of order 6 either. You cannot do that. Of order 12, can you do that?
Yes.
1, 3, 8. That's A4.
Okay,
Yeah.
so as long as you add up the sizes and they're equal to
And they're a group. There also should be a group, right?
Yeah.
You could form. You might be able to form, right? You might be able. So 8, for example, a conjugate class of size 8, but that's not a group because you don't have the identity.
But technically, like if as long as we're putting in the identity, will they all?
Not necessarily. Take one and in that case it's not. You don't get that, right? Because if you add 1 and 6, you don't blend them divisor. But in general sense.
But I mean, like let's say we take the identity and then use like basically add them up to make sure it's a divisor. So then how do we know?
You have to check it's a subgroup first. This one, if you had that, you were lucky here that you got this. It's a pure luck. It's not like it's a. You were lucky that this one in 3 you got a subgroup for 4. You were lucky that you got a subgroup. Right? This is the luck here. This is the good part for S4. In Sn, you don't have that. If n is different than 4, the only normal subgroups are 1, A3, and An and Sn. And Sn. Right? If n is bigger or equal to 5, say. These are the only normal subgroups. S4 is special because you have that.
Okay, so eight, like normal subgroups of order 8, we can't
Have a normal subgroup.
Yeah. And then 2 we said we can have. We have a 1 of order 4, which is the only one we can. Yeah. Yeah. And then it's normal subgroup of order 12, 44. Then you just have S. And will we like, would we, I mean, then have to justify this?
No.
Like, okay, like we get, like, we just know like what he is. Mhm.
I asked you, write down the conjugate class of S4,
Mhm.
and then give a list of the normal subgroups of S4, and I will tell you justify why are your subgroups subgroups. Okay, I won't tell you justify these are. See what I'm saying? Yeah, exactly. Justify why B is a subgroup. You just don't have to justify why these are the only possibilities because it can take some time. Okay.
And for S5, is it the same principle?
But you will just get one A5 and S5.
So it's just because S4 is special then.
S4 is special. S4 is nice. This is why you have a surjective map from S4 to S3, but you don't have from S5 to S3.
Do you have from S3 to S4?
Surjective, no, you cannot have. Because S3 has smaller size than S4. Injective you do, yeah. S3 injects into S4. No, it's 1 is the identity, B, this one, A4, and S4. Yeah, and sorry, sorry. No, I just want you, oh, depends what the question is asking. No, because I didn't prove that A5 is simple, right? The way you prove that A5 is simple is by conjugate sequences. So I'll tell you, write down the normal subgroup of it. Write down the conjugate class of S5 and find the normal subgroups of S5. Yeah. Let me just see that. Oh man, in the chat, very active. Let's see.
How many viewers?
Can you prove surjective homomorphism? Okay. I know you've covered it, but can you go over how to prove it again? Okay. Do we need to know the second and third isomorphism theorem? I know you answered that we need the first, but I forget what you said. Okay. So you don't need the second and the third. Okay. The second and third, you may omit them. Okay. The first, you may need to use it, yes. You will need to use it, but not to prove it. Okay, can you prove the surjective homomorphism from S4 to S3? Okay, I'll do that. For what type of statements or step can we refer to the homeworks or notes? Depends. Unless it's the question I'm asking you to do, then you can refer to the homework. Okay, if you need a part from the homework, you can refer to it. But it will be clear, so don't worry too much about this. Okay, let's go the S4 to S3 examples. Yeah. I'll do it because someone asked. Okay. Yeah. Okay, are you with me? The person who asked, are you with me? Cayley's theorem. Yeah, you need the Cayley's theorem, yes. So S4 to S3, I will cover that now. Okay. Great. Let's do this. Really, there are many ways to do it. There are many ways to do it. Let's go S4 to S3. So how do you want to start? Really, I mean, it's your call. It's how do you you want to find all the subgroups of order 8 in S4 or one of them? You can do many ways. You can do it like we did in homework 9 or like we did in homework 8. Which one do you prefer? I could do both. I could do either of them. Either. Okay, great. Let's do where I find. So first of all, I have a subgroup of order 8 in S4. I'll call it, let's say, H. And it's the group of symmetries of that square. Now, what are the symmetries of that square? If you really look at this, you have the vertical line, you have the horizontal line, first diagonal, reflection along the first diagonal, and reflection along the second diagonal, and the rotation. Okay, is that clear? Is that clear? Just waiting so that the sound arrives, reaches the. Yeah, okay, so let's write them down. Do you want me to write them down, or that's good? I could write them down. So what is the rotation? So you have the identity, you have the rotation 1, 2, 3, 4. You have the square of this rotation, which is 1, 3, 2, 4. You have the cube of this rotation, which is 1, 4, 3, 2. And then you have the diagonal reflection. When you reflect along D1, you flip 2 and 4 and you keep 1, 3 fixed. When you reflect along when you reflect along D2, you switch 1, 3 and you keep the 4 fixed. And then the vertical one, it's 1, 2, and you flip 3, 4. And the horizontal one, it's 1, 4, 2, 3. Okay, these are all the elements of H. Okay, are we good here? No, it's not done now. Unless you got it. You want me to continue or? So the action of S4 on S4 mod H, by you take sigma and S4, say G and S4, cosine XH, induces a homomorphism rho from S4 to the symmetric group of G mod H, of S4 mod H, which is isomorphic to S4. Isomorphic to S3, sorry, S4 mod H. And the kernel of this homomorphism okay, the kernel of rho will be contained in H. This is the coset representation. Now, H is not normal in S4. You can see that by just taking an element that is not in S4 and conjugating an element here, and see that you're lined outside. So for example, 1, 2 doesn't belong to S4. 1, 2 times 1, 3 times 1, 2. What is that? 2 goes to 1, 1 goes to 3, 2 goes to 3, and 6. So this is 2, 3. Doesn't belong to H. 2, 3 doesn't belong to H. So H is not normal in S4. Hence, the size of the kernel is strictly less than the size of H, which is 8. Now, and you also know by the first isomorphism theorem, D modulo the kernel of rho, the index of kernel of rho, divides 6, which is the size of S3 really. Now you also know that G kernel of rho is strictly bigger than GH, which is 3. H has order 8. So you must have G per row divides 6 and is strictly bigger than 3. So G per row is 6. So G is S4, sorry. Let's just S4. 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 So rho is surjective. And Kuro has order 4. Now, if Kuro has order 4, what's the only normal subgroup of S4 of order 4? It's just the V. So Kuro is V. Since is the only normal of size 4 in S4. Okay, is that good? Okay. And there are other ways to do it. I think in the practice final, I give it to you another way as well.
So that's the proof. There's
Surjective from S4 to S3. Yeah.
Maybe proved Ceylon's theory.
Yeah.
But the thing is that it wasn't officially named Ceylon's theory.
Yeah,
It was very
no, I won't ask you. I put it in a marginal way. Prove that K could be 0. Yeah, but in Ceylon's first theorem, I assume that K is not 0.
Yeah.
So, we don't have the first.
No, I know Ceylon's first theorem we don't need to, but I think there was another something else that
With P groups? Yeah, I wouldn't worry too much.
inducting.
Yeah, the one by induction. I wouldn't worry too much about it.
Yeah, they did.
So, like, if I ask you to show the proof of the converse of Lagrange holds for P
Yeah, I
groups.
think so.
Yeah, I wouldn't worry.
Like the result, yeah.
But I wouldn't worry too much about the proof. But I can ask you small parts of it, not the induction. Fair. I mean, actually, the induction is fair, but I won't. Yeah. Okay.
Thank you.
No problem. Let's see if people have questions here. Okay, perfect. Oh, no problem. Well, the practice finals come the solution. No, I'll go over it Thursday. I want you to go and try it on yourself with on your own for 3 hours. Sit down and try and see how much you can do. No, I don't think it's you can do well in the final without doing the practice final. It's not a. I mean, I wrote both, so I will not write something useless. But it's not like if you do well on this one, then you will do well on the second one. No, it's totally uncorrelated. I would not count on it. Like studying the practice, if you just study the practice and you go to the final, disaster. I mean, the reviews are mostly I go over homework, nice problems. So these are fair games. Nice. Yeah, these are nice problems. A lot of group actions, fair game. Yeah. I mean, I usually don't look at the exam and say, what did I do in the exam? And, not do it. So it could be something, yeah. Oh, question here. No, I would say it's more difficult. Yeah, so I mean, at the beginning, I said that if I create a practice final, it would be a lot harder. Now it will just be harder. It will just be hard, not by far harder, but you will see that it's going to be kind of the. I mean, yeah, difficulty. I think it will be a bit harder and a bit longer, just in case, so that no one tells me, oh, the practice was easier. Okay, so that no one tells me that.
We have to choose which one studying or do like practice final.
Studying.
Studying, definitely. Definitely. Study, definitely. Don't,
Is this the room to know?
both. Yeah, it's I can easily ask you a question from the homework. Like a question from the homework could come up. That's yeah. All the questions. I mean, 7, 8, 9 were all graded, right? To my memory, yeah, 7, 8, 9 were all graded for a reason, right? 7, 8, 9, I graded them all, and you knew which one to hand in. Like I didn't tell you hand in everything. I mean, I think all of it was graded. All of 7, 8, 9 were graded to my memory.
Yeah, I have a question.
Yeah. Okay. Yeah. You made me sure. Yeah. Don't worry. Yeah.
And see, we did 1, 2, 1, 3, 1, 2 equals 2, 3.
Yeah.
That's the x something x inverse equals. So you know, like to prove it's just normal subgroup.
Yeah.
What's like the actual things?
Where here? This one here.
It's just there. But in terms of letters, you know, like the definition of normal subgroup is like is what xn
X. So G X G inverse
is equal to.
doesn't belong to H. So if it were normal, then G X G inverse would belong to H. And this one doesn't belong to H. X belongs to H.
G belongs to H.
G doesn't belong. No.
G belongs to G.
G belongs to G. If it belongs to H, then it will belong to. But G X G inverse will not belong to H.
It's 2, 3. And
H. Look at H. Do you have 2, 3?
No.
No. Were all questions from homework 9 graded? Yes, but I grade them for completion. Yeah, I grade them for completion. I mean, I think I gave the answer to homework 9, right? I gave the answers to homework 9, so I just graded for completion. Okay, more questions from people attending? And 3 on homework 8.
Question 2.
What's question 2?
This one.
Question, the whole exercise?
Yeah.
Yeah, okay.
Thank you.
So, what does it say? Solutions are important for this one though, right?
But yeah, they use like some random lemmas though.
Yeah.
Oh, okay.
So
I can show you if you want.
Just, yeah. You have the.
Yeah, let me just.
yeah, the solutions are log and
What is it? Oh, wow. Solution. It's a bit down here.
No, the question 2 doesn't have a lemma. I mean, it's short. Yeah, it has a lemma, but it's short. Okay.
Oh.
Yeah. So I mean, I'll go through it. So let's see. Thank you. So what first? What's the stabilizer of G star S? Right. The stabilizer of G star S is just G stab S G inverse. That's what he proves. Should I prove it? Okay. Prove. X belongs to stab G star S if and only if X star G star S is equal to G star S, right?
Yep.
If and only if XG star S is equal to G star S, and then put an inverse here, star inverse, you get G inverse XG star S is equal to S, right? If and only if G inverse XG belongs to step S, if and only if X belongs to G step S G inverse. So these two are equal. Okay? And then if the kernel of the induced group homomorphism, what is this? Kernel of rho will just be the intersection as S is in S of step S, right? This is the kernel of the induced homomorphism. Now, if the action is transitive, you can just any S can be written right. If the action is transitive, any S in S will just be G star S0, and then you will be intersecting them on G. And then what is that? This is just the intersection. Okay? H being step S0. Okay? Now the second one. Show that if G acts transitively on S, then rho of G is a transitive subgroup of sim S. Right? So what is rho? Rho sends G to sim S, and it sends little g to lambda g, where lambda g is from S to S. It sends little s to G star S. Right? Now, what does S is transitive? So if S1, S2 belong to S, and there exists, let's say, G in G, such that G star S1 is S2. Right?
Yeah.
So lambda G of S1 is equal to S2.
The first one is because it's transitive.
Yeah. The second one is by definition of lambda G. Well, this means that you can find an element of rho G that sends S1 to S2. So rho G is transitive. It's lambda G and rho G. And rho of G is transitive subgroup of sim S. Okay? I mean, I started grading the bonus, but I think it will take some time. I hope if I'm done before Thursday, then good. If I'm not, then I said yes, 2% something. Maybe a bit more. Maybe no. It's actually two. Yeah,
You told me.
yeah, maybe a bit more. Something around that. Yeah. What was said before about P groups? I don't know. The girl asked you something about P groups, and you said she didn't need. Oh, just the converse of Lagrange, the induction part. I won't ask you that, but you should know that any part before, any part other than the induction part, I can ask you about it. No, the for P groups. Look at the proof of P groups, the converse of Lagrange. Then I can ask you a part of it. Yeah, that's it. That you can find an element for any S1 and S2. You can find an element in lambda G, an element in rho G that takes S1 to S2. That's what I did. Yeah, this one. Lambda G of S1 is S2. And lambda G is an element of rho G. Yeah, it is. No, from G to sim S. Induced by the action. It sends G to lambda G, where lambda G is given by lambda G of S is G star S. Now, G acts transitively on S. So if S1 and S2 belong to S, there exists a G such that G star S1 is S2, right? So lambda G of S1 is equal to S2 by definition of lambda G. Now lambda G is an element of rho G. So rho G will be a transitive subgroup of sim S. Okay? That was meant to be this way. It's a small proof. Is there only one question? No, P groups is lots of questions. P groups. Yeah, P groups have lots and lots of questions. Yes. P groups, no, someone asked if P groups has only one question. No, P groups have lots and lots of questions, right? Silo theorems are in P groups. The center of P group is non-trivial. Things like that. So I can ask you, show that a P group has a normal subgroup of order P, for example. Things like that.
Is ZG, no, that's the middle.
The
Middle.
center, the center. Yeah.
But it's subgroup. Sorry.
I'll just, yeah.
That is the center the same as a fixed point? Or is it fixed point the same as singleton orbit?
Well, depends. Fixed point is the same as singleton orbit, but the center is the set of fixed points for the action of G on itself by conjugation. So when G acts on itself by conjugation,
So
what is the set of fixed points? The center.
G,
Inverse is equal to X for all G and G. So this means that Gx is equal to Xg for all G and G.
so the left and the right cosets.
No, not more than that. Not cosets. G little x. So Gx is equal to Xg for all G and G. Means that X belongs to Zg.
So X is the identity.
No, X is commutes with everything. You cannot say it's the identity.
It means with everything. It's special.
Yeah, but it's not necessarily the identity. Take any abelian group.
Wait, so X can use everything, not G.
So Gx is equal to Xg for all G and G.
Or G and G. So
X will
X.
commute with Cameron. Exactly. So X is in the center. So the set of fixed points is the center of G acting on itself by conjugation.
yeah.
Now, if G acts on a normal subgroup H by conjugation, what is the set of fixed points?
Gx, G inverse equals
Same
X,
thing.
G, X.
X, yeah. But X will belong to H as well. Is not any G. So the set of fixed points is just H intersection ZG. Very good.
Wait, but prove the same as normal subgroup. Say
No, I'm saying you have a normal subgroup.
Yeah.
Show that G acts on it by conjugation. This is homework 7.
it's 2A or something, 2B, isn't it?
Something like that. Yeah. But I posted the solution. I posted the solution. You can see the solution. Yeah, I did. No.
Video.
Yeah.
I didn't-
Lecture
Oh,
by
on
lecture.
YouTube.
Lecture by lecture. No, lecture by lecture. You will see all the links. You don't monitor the lecture by lecture, do you? Yeah, but lecture by lecture, I post everything. It's way better. I post the links and I post everything else. Yeah, P group, yeah. Yeah. Cayley's theorem on the discussion board, you said you need to know. Need to know what is it? What do you mean? Oh, I mean, how do you? The generalization of Cayley's theorem is just the homomorphism induced by a group action. Okay, this is what I mean, I can ask you to prove, like, show that the action of G in S induces a homomorphism from G to sim S, and then I can tell you deduce Cayley's theorem. No, I can ask you how to prove it through group actions as well. Yeah. I mean, homework 7 has applications on Cayley's theorem. The statement, yes, not the proof. So the Cauchy's theorem is just actually the statements or the proof. Okay, you guys have questions? You want to ask or?
Two small questions.
Yeah.
One is, just in general, do we have to show that rho of G is a group? Or we
No,
have
no, that's okay. That's okay. You don't need. So the question is that do we have to show that rho of G is a subgroup? No, you don't need to. You can assume it if rho is a homomorphism. Yeah.
If it-
Mhm.
Or that's for the S3.
No, depends on the question. If I If I give you something like that, I'll be clear. You are allowed to use what you have seen in the lecture notes or the homework. Or I will tell you, you are not allowed to use, or you should prove any. So the way I'll format it, you should prove any statements if it's going to be in there. You should prove any statement concerning the normal subgroups of S4.
And then we would just do what we did before, table.
You could do that with the tables, or you can take all the conjugates of H. You know that there are 3 conjugates of H by Seelow's theorem, right? Since H is not normal, you have 3 conjugates. You label them, right, by removing this, right? And you take the intersection. Or what you can do, you say that you know that the kernel is a normal subgroup, and you have your subgroup H. What is the only possible normal subgroup of H that is normal in S4?
Oh, the constant class.
Exactly. Exactly. So that's one way. That's another way to do it. But yeah, so usually I'll be clear. Exactly, because the kernel is contained in H. Exactly. The kernel of the coset representation is contained in H. If I ask you to, if I tell you that you're not allowed, then you should prove everything you have. Or yeah, I mean, if you have a question like that, I think I'll be clear with the directives. I'll be clear with what to the instructions you have to follow. Okay. More questions? People attending online, do you guys have more questions? Oh, so she asked if whether we can assume this thing that this is the only normal subgroup size 4 in S4 without proving it. I said that depends on the question. No problem. Yeah. So, yeah, is that good? Alexia, is that good? No problem. Okay. Great. Okay. We have more people. Questions? Great. Let's shut this down then. Yeah, it's 3 hours. I started to close my eyes.
You're an adult.
Thank you for answering all. No problem. No problem. Yeah, by the way, you guys can fill your course evaluations. No, but did you guys fill them in? Yeah, please. Fill them in. It's important for me. Be honest, I'm not. Yeah. No problem. Please fill in your course evaluation. I forgot.
What's it tomorrow?
Yeah, but I said it on Monday, right? Did I say it on Monday?
I did it last week.
Okay. Did I say on Monday? Friday I did not mention. Yeah.
Do it again.
Yeah, I'll do it again. But tomorrow is the deadline. The math department doesn't allow course evaluations to be filled after final exams for a reason. You know. It's a they don't allow to fill the. There's a good reason they do that. So they don't fill.
Something happened.
I don't know, but in general, like some departments allow to fill course evaluations during the final exam. I don't know what departments. Comp they do. Course eval in your comp. Okay, yeah, the math department doesn't allow. Midline. So tomorrow midline. Tomorrow midnight is the deadline. No, I said midline. You said deadline. Yeah, tomorrow midnight is the deadline. But the math department is very strict that it's the last. Oh, really? I don't know how to do this. Oh, okay, that's nice. Okay. I see. So like, yeah, no, so usually in your comp class, they'll just wait after the final.
Oh, the homework.
Is it like machine learning? Oh, okay.
Two. Yeah.
Okay, let's not talk. Let's not talk here. Let's not talk. Let's not talk on the public stream. Okay, guys. Anybody attending has a question? Virtually. Anybody attending virtually has a question? Okay, great. We'll shut this down. And then tomorrow, I'll be here 6 to 7 as well. Do some problems. Thursday, do the practice. Okay, good night, everybody. Bye bye. And